Deeper than the cold, older than memory, Antarctica keeps its secrets well. Far below, sunlight never touches the ground. Thick ice, stretching over kilometers, has crushed the land beneath it for millions of years. Hidden underneath are entire landscapes, mountains, valleys, rivers flowing in darkness, and lakes that remain liquid, warmed by Earth's deep heat. The ice holds pieces of the past, air from thousands of years ago, dust from forgotten volcanic eruptions, even tiny clues of life that once thrived. In the early 2000s, scientists used radar to see beneath the surface. What they found was astonishing. Massive mountain ranges, huge underground lakes the size of countries, and signs of microbes that live in total isolation. These discoveries showed us that there's an entire hidden world under the ice. Antarctica stands as the planet's most immense single body of ice, an unparalleled frozen expanse that dominates the Earth's southernmost region. Its sheer scale is difficult to grasp, covering an area of roughly 14 million square kilometers, or about 5,400,000 square miles. To put this into perspective, this ice-covered continent is significantly larger than the entire continent of Europe and nearly double the size of Australia. The vastness of this icy domain is not merely horizontal, its vertical dimensions are equally staggering. The average thickness of the ice across Antarctica is approximately 1.8 kilometers or 1.1 miles. In some regions, particularly within the East Antarctic ice sheet, the ice can reach depths exceeding 4.5 kilometers or nearly 3 miles, representing a colossal accumulation of frozen water. This immense volume of ice, estimated to be about 30 million cubic kilometers, makes Antarctica the largest reservoir of frozen fresh water on Earth. Its sheer weight is so great that it has pressed down the continental landmass beneath it by hundreds of meters, a phenomenon known as isostatic depression. The land surface under the ice sheet lies mostly below sea level, even though Antarctica is a continent with mountains, valleys and plains, all hidden beneath the glacial shroud. The Earth's fresh water is overwhelmingly stored in this single location. Out of all the fresh water present on the planet, an astonishing 90% is locked away within Antarctica's ice. This includes both the water in glaciers and ice caps. The remaining 10% is distributed across other ice masses, groundwater, lakes, rivers, and the atmosphere. This makes Antarctica an exceptionally critical component of the global water cycle and a primary determinant of future sea levels. If, hypothetically, the entire Antarctic ice sheet were to melt, global sea levels would rise by approximately 60 meters, or nearly 200 feet. Such an event would redraw the world's coastlines, submerging numerous major cities and low-lying landmasses. The stability of this vast ice sheet is therefore of paramount importance to the entire planet's coastal populations and ecosystems. The ice itself is primarily composed of fresh water, accumulated over millions of years from countless snowfall events. Unlike sea ice, which forms from frozen ocean water, the Antarctic ice sheet is terrestrial ice, originating from precipitation that falls on land and compacts over time. This distinction is crucial as melting sea ice does not significantly contribute to sea level rise, whereas the melting of land-based ice directly adds water to the oceans. The formation of this ice giant is a story spanning tens of millions of years. Antarctica began its journey towards its current frozen state roughly 45 million years ago, when the continent separated from South America and Australia, allowing the Antarctic circumpolar current to develop. This powerful ocean current flowing eastward around the continent isolated Antarctica from warmer waters, leading to its gradual cooling and the eventual onset of extensive glaciation. By approximately 34 million years ago, the continent was largely covered by a vast ice sheet. This long history of continuous ice accumulation has resulted in the incredible depths and volumes observed today. The ice sheet is not a uniform block. It is composed of two main parts, the larger East Antarctic ice sheet and the smaller West Antarctic ice sheet, connected by a high ice ridge. The East Antarctic ice sheet is the older, thicker and more stable of the two, resting largely on land above sea level. The West Antarctic ice sheet, in contrast, is more dynamic and grounded, mostly below sea level. making it potentially more vulnerable to changes in ocean temperatures. The Antarctic Peninsula, extending northward, represents the continent's most northerly and rapidly warming region, with numerous smaller ice caps and glaciers. The sheer mass of the Antarctic ice sheet exerts a gravitational pull that is so significant it actually affects global sea levels. The mass attracts ocean water towards the continent, creating a slight bulge in sea level around Antarctica. If this ice mass were to decrease, the gravitational pull would weaken, causing sea levels in distant parts of the world to rise even more than the average global rise, while sea levels closer to Antarctica might experience a relative fall due to the reduced gravitational attraction. This complex interplay between ice mass, gravity, and ocean dynamics highlights the interconnectedness of Earth's systems and Antarctica's central role within them. The ice giant is a dynamic entity, constantly gaining mass through snowfall at its surface, and losing mass through iceberg carving and melting at its edges. The balance between these processes, known as the mass balance, is a critical indicator of the ice sheet's health and its contribution to global sea level change. Scientists employ various methods, including satellite altimetry, gravity measurements, and airborne ice-penetrating radar, to monitor these changes with increasing precision. The unique environment of Antarctica, characterized by extreme cold, high winds, and perpetual ice, makes it an unparalleled natural laboratory for scientific research. Its isolation from major human populations means its ice contains some of the purest records of Earth's past atmosphere, free from modern industrial pollution. The ice cores drilled from deep within the ice sheet provide invaluable insights into ancient climates, atmospheric composition, volcanic activity, and even past solar cycles, spanning hundreds of thousands to millions of years. Each layer of ice acts as a chronological archive, preserving tiny air bubbles that hold samples of the atmosphere from the time the snow originally fell and compacted into ice. The sheer vastness of the ice giant means that significant portions of the continent's underlying bedrock remain largely unexplored. Scientific expeditions using specialized ice-penetrating radar technology have begun to map the hidden topography beneath the ice, revealing vast mountain ranges, deep canyons, and even extensive subglacial lake systems. These discoveries have transformed our understanding of the continent's true geography, which is vastly different from the ice-covered surface. The presence of these liquid lakes beneath kilometers of ice challenges conventional notions of where life can exist, and raises profound questions about potential unique ecosystems isolated for millions of years. The ice giant's surface features are a testament to the powerful forces at play. Vast flat plains stretch for hundreds of kilometers, punctuated by dramatic ice domes where ice thickness is greatest, and by treacherous crevasse fields where the ice flows over uneven terrain. Sastrugi, sharp, irregular ridges of snow formed by wind erosion, create a perpetually changing, undulating landscape across the interior. Icefalls, analogous to waterfalls on land, occur where the ice flows rapidly over steep slopes, breaking into chaotic blocks. These features are not merely aesthetic, they are indicators of the complex internal dynamics of the ice sheet. Near the coast, the ice flows into the ocean, forming immense floating ice shelves. These ice shelves, such as the Ross Ice Shelf and the Ron-Filchner Ice Shelf, are extensions of the continental ice sheet, acting as a buttress that slows the flow of ice from the land into the sea. Their stability is crucial for the overall stability of the ice sheet. When ice shelves collapse or thin, the ice behind them can accelerate its flow towards the ocean, contributing more rapidly to sea level rise. This phenomenon has been observed on the Antarctic Peninsula, where several ice shelves have disintegrated in recent decades due to warming ocean and air temperatures. The internal structure of the ice is not uniform. It comprises layers of ice crystals of varying sizes and orientations, along with trapped air bubbles and occasional layers of volcanic ash or dust. The orientation of ice crystals, known as ice fabric, influences the way the ice deforms and flows. Deeper ice, under immense pressure, exhibits a preferred orientation of crystals that allows it to flow more easily. The trapped air bubbles, ranging from large pockets near the surface to tiny high-pressure spheres at depth, are invaluable for paleoclimate research. As the ice compacts, these bubbles seal off, preserving a pristine sample of the ancient atmosphere. Scientists can analyze the composition of these air bubbles, including concentrations of greenhouse gases like carbon dioxide and methane, to reconstruct past atmospheric conditions and understand the natural cycles of Earth's climate. The density of the ice increases with depth as snow transforms into firn and then into solid glacial ice, reaching a density close to that of pure ice, approximately 917 kilograms per cubic meter. This transformation is a slow, continuous process, gradually squeezing out air and reorganizing the water molecules into a crystalline structure. The base of the ice sheet presents another realm of mystery and complexity. It interacts directly with the underlying bedrock, sometimes flowing over smooth, polished surfaces, and at other times grinding over rough, rocky terrain, causing erosion. Geothermal heat flowing from Earth's interior warms the base of the ice, which, combined with the immense pressure, can lead to basal melting, forming a thin layer of water that lubricates the ice flow. This basal water plays a crucial role in regulating the speed of ice streams, which are fast-flowing rivers of ice within the slower-moving ice sheet, channeling ice towards the coast. Understanding the dynamics at the ice-bedrock interface is fundamental to predicting how the ice sheet will respond to future climate change. The physical properties of the bedrock, including its geology, topography, and thermal characteristics, significantly influence ice flow and stability. Some areas beneath the ice are known to have active volcanoes, which release significant amounts of heat, contributing to basal melting and the formation of subglacial lakes. These volcanic heat sources represent localized hotspots that can influence ice dynamics over substantial areas. The sheer scale of the ice giant creates a unique microclimate above its surface. The high albedo, or reflectivity of the ice surface, reflects a large proportion of incoming solar radiation back into space, contributing to the planet's energy balance and maintaining the cold conditions. The katabatic winds, dense, cold air that flows downslope from the high interior plateau towards the coast, are a defining characteristic of Antarctic weather. These winds can reach hurricane force, shaping the ice surface and transporting snow, further sculpting the vast landscape. The isolation of Antarctica, surrounded by the Southern Ocean and its powerful circumpolar current, has largely protected it from external influences, allowing the ice sheet to grow to its present formidable size. This isolation also contributes to the preservation of its hidden secrets, making it a pristine environment for geological, biological, and climatological discoveries. The ice giant is not merely a static, frozen mass. It is a living, breathing component of the Earth system, influencing global climate, ocean currents, and sea levels in profound ways. Its ongoing evolution in response to global environmental changes makes it a focal point of scientific inquiry and a key indicator of the planet's future trajectory. The secrets it holds are not just historical curiosities, they are vital pieces of the puzzle for understanding our planet and preparing for the challenges that lie ahead. The sheer magnitude of this frozen continent, its unparalleled freshwater reserves, and its hidden depths continue to inspire awe and drive scientific exploration, revealing layer by layer the wonders that lie beneath its formidable icy exterior. Every kilometre of ice, every cubic metre of frozen water, contributes to the majesty and mystery of this global ice giant, a true testament to the power of nature. The process by which ice forms and accumulates in Antarctica over vast stretches of time is a fundamental aspect of understanding what lies beneath its surface. It begins with the seemingly simple act of snowfall, yet the transformation of individual snowflakes into a continental ice sheet spanning millions of square kilometres is a complex and lengthy journey. Snow falls across the vast expanse of Antarctica, primarily in the interior, where temperatures are consistently below freezing. The snow here is typically dry and fine, lacking the moisture content often found in temperate snow. This constant precipitation, though relatively light in the continent's interior compared to coastal areas, accumulates year after year, century after century. The rate of snowfall varies significantly across the continent. Coastal regions, especially those influenced by cyclonic storms, receive more snowfall than the extremely cold and dry central plateau, which can be a polar desert in terms of precipitation. Despite low annual snowfall in many areas, The crucial factor for ice sheet growth is that virtually no snow melts. Nearly all of the precipitation remains on the surface, gradually building up. As new layers of snow fall, they bury the older layers beneath them. This overlying weight begins the first stage of transformation, the compaction of snow into firn. Firn is an intermediate state between fresh snow and dense glacial ice. Initially, the snow crystals are light and airy, with a high proportion of trapped air between them. As the pressure from successive snowfalls increases, the delicate snow crystals are crushed and recrystallize, becoming more compact and rounded. The air spaces between them decrease, and the density of the material increases. This process, known as firnification, involves sintering, where ice grains bond together at their points of contact, gradually eliminating pore space. The firn layer can extend to depths of many tens of meters, typically 50 to 100 meters, depending on accumulation rates and temperature. Within this firn layer, the air remains connected to the atmosphere through a network of pores. This allows for some exchange of gases, but as the firn compacts further, these pores begin to close off, trapping samples of the ancient atmosphere within discrete bubbles. The temperature of the snow and firn also plays a role. Colder temperatures slow down the recrystallization process. The transition from firn to true glacial ice occurs when the pressure of the overlying layers becomes so immense that all the remaining air pores are squeezed out or sealed off as isolated bubbles. This usually happens at depths beyond 100 meters, sometimes extending to several hundred meters. At this point, the density of the ice approaches its theoretical maximum, roughly 917 kilograms per cubic meter. The formerly distinct snow crystals have been entirely recrystallized into larger, interlocked ice crystals, forming a solid, bluish glacial ice. The trapped air bubbles, now sealed off from the atmosphere, contain pristine samples of ancient air, preserving the exact atmospheric composition from the time the snow fell. These air bubbles are invaluable for paleoclimate research, allowing scientists to reconstruct past atmospheric concentrations of greenhouse gases, such as carbon dioxide and methane, providing direct evidence of Earth's climate history. The process of compaction also influences the internal structure of the ice, as individual ice crystals tend to align themselves in a preferred orientation, forming what is known as ice fabric. This fabric affects how the ice deforms and flows under stress, influencing the overall dynamics of the ice sheet. This continuous process of snow deposition, firnification, and ice formation has been occurring in Antarctica for millions of years. Each year's snowfall adds a new layer, creating a chronological record within the ice sheet. In areas of high accumulation and relatively stable ice flow, these annual layers can be distinguished, allowing scientists to determine the age of the ice at different depths. Ice core drilling is the primary method used to extract these invaluable records. Long cylinders of ice are retrieved from deep within the ice sheet, providing a continuous stratigraphy or layered record of past climate and environmental conditions. The longest ice cores extracted in Antarctica penetrate more than 3 kilometers deep and extend back in time for over 800,000 years. In some regions, especially in the blue ice areas where ancient ice is brought to the surface through natural flow, scientists have found ice that is estimated to be over 2.7 million years old, providing insights into an even more distant past. This immense accumulation over vast periods has sculpted the continent, burying entire landscapes and preserving them in a frozen state. The immense layers of ice effectively bury whatever was present beneath them, creating a time capsule of Earth's past. Before the extensive glaciation of Antarctica, which began around 34 million years ago, the continent was a very different place. Geological evidence, including fossilized plants and animals found in exposed areas, indicates that Antarctica once supported lush forests and diverse fauna, including dinosaurs, during warmer geological epochs. As the climate cooled and ice sheets expanded, these pre-existing landscapes, including mountains, valleys, rivers, and possibly even coastal plains with ancient life forms, were gradually overwhelmed and submerged by the advancing ice. The sheer weight of kilometers of ice then pressed down on these buried features, preserving them under enormous pressure and cold. This process transformed the continent into the icy realm we know today. with much of its true topography and ancient history hidden from view. The ice effectively acts as a protective shield, isolating the underlying bedrock and any embedded materials from the erosive forces of wind, water, and biological decomposition that would otherwise alter or destroy them on the surface. The burial process has profound implications for understanding Earth's geological history and the evolution of its surface. The ice sheet does not simply sit on the land, it actively reshapes it through processes of glacial erosion. As the ice flows, it scours the bedrock, plucking away loose rocks and abrading the surface with embedded debris. This action creates distinctive landforms such as U-shaped valleys, cirques, and fjords, which are only revealed when the ice retreats, or are mapped through ice penetrating radar. The material eroded by the ice is transported and deposited as till or moraines, forming new geological features. This continuous cycle of erosion and deposition contributes to the creation of unique subglacial topographies, some of which are surprisingly complex and rugged, featuring vast mountain ranges like the Gamburtsev Mountains, hidden beneath thousands of meters of ice in East Antarctica. The pressure exerted by the ice also causes the underlying continental crust to depress, a phenomenon known as isostatic loading. If the ice were to melt, the land would slowly rebound, rising back to its original elevation over thousands of years, a process called post-glacial rebound. The preserved state of materials beneath the ice is a direct consequence of the extreme conditions prevalent in Antarctica. The continent's extraordinarily low temperatures, reaching as low as -89.2 degrees Celsius or -128.6 degrees Fahrenheit, effectively freeze any organic or inorganic material in place. This deep freeze halts the processes of decomposition that would typically break down organic matter in warmer environments. The lack of liquid water in most areas beneath the thick ice also inhibits chemical weathering and biological activity that rely on water. Furthermore, the immense thickness of the ice provides isolation from surface atmospheric conditions, creating a stable, protected environment. The absence of oxygen beneath much of the ice sheet, particularly in deeply buried layers or subglacial lakes, creates anaerobic conditions which are highly conducive to the preservation of certain types of organic material and microorganisms. This combination of extreme cold, pressure, and isolation effectively creates a natural deep freeze, preserving ancient landscapes, geological features, and potentially unique life forms for millions of years. One of the most remarkable forms of preservation within the frozen deep is that of ancient air. As snow compacts into firn and then into glacial ice, the air trapped between the ice crystals becomes sealed off in tiny bubbles. These bubbles provide direct samples of the Earth's atmosphere from the time the snow originally fell. Scientists can extract and analyze these air bubbles to determine the precise composition of the atmosphere at various points in Earth's history, going back hundreds of thousands of years. This includes the concentrations of greenhouse gases such as carbon dioxide, methane, and nitrous oxide, allowing researchers to reconstruct past climate cycles and understand the natural variability of the Earth system. These ice core records demonstrate a strong correlation between greenhouse gas concentrations and global temperatures over geological timescales. Beyond gases, the ice also preserves dust particles, volcanic ash, pollen, and even cosmic particles, providing information about ancient wind patterns, volcanic eruptions, vegetation, and extraterrestrial events. The chemical composition of the ice itself, particularly the ratios of stable isotopes of oxygen and hydrogen, acts as a thermometer, indicating past temperatures when the snow was formed. The freezing of landscapes has also led to the preservation of ancient hydrological systems. Beneath the vast ice sheets, scientists have discovered an extensive network of subglacial lakes and rivers, some of which are enormous, like Lake Vostok. These lakes remain liquid despite being buried under kilometers of ice due to a combination of geothermal heat from Earth's interior and the insulating effect of the thick ice above, which traps heat. The immense pressure from the overlying ice also lowers the melting point of water, allowing it to remain liquid at temperatures slightly below 0 degrees Celsius. These subglacial water bodies are isolated from the modern atmosphere and surface contamination, making them pristine environments. The discovery of these lakes has opened up new avenues for scientific inquiry, including the search for unique microbial life forms that have evolved in complete isolation for millions of years, adapting to extreme conditions of darkness, high pressure, and limited energy sources. The potential for discovering novel biochemical pathways and entirely new branches of the tree of life within these hidden aquatic environments is a driving force for current scientific exploration. The stability of these preserved features beneath the ice is directly linked to the dynamics of the ice sheet itself. In regions where the ice is stable and flows slowly, the ancient layers and buried materials remain relatively undisturbed. However, in areas of rapid ice flow, such as ice streams, or near the margins where the ice interacts with the ocean, the forces of erosion and deformation are more pronounced. The frozen deep acts as a massive natural archive, holding records of Earth's past geological, climatic, and biological evolution. Every kilometre of ice, every layer, every trapped air bubble contributes to this extraordinary repository of information. The cold, dark, and high-pressure environment beneath the ice provides conditions for preservation that are unparalleled anywhere else on Earth. It protects ancient landscapes from weathering, organic matter from decay, and atmospheric gases from mixing with modern air. This continuous freezing and burial process ensures that secrets from Earth's deep past remain intact, awaiting discovery by future generations of scientists. The exploration of this frozen deep continues to reveal surprising insights into the planet's history and offers clues about the potential for life in extreme environments, both on Earth and beyond. The very act of ice formation and its subsequent accumulation over vast periods is a testament to the immense power of natural processes in shaping the planet and preserving its hidden truths. The lure of a great southern continent, Terra Australis Incognita, had captivated imaginations for centuries, long before any human laid eyes on Antarctica's frozen shores. Early maps depicted a vast landmass in the southern hemisphere, often for balance with the northern continents, more a theoretical construct than a geographical certainty. Mariners from the 1500s onwards occasionally ventured into high southern latitudes, but their primary focus was trade routes to Asia, or the search for new lands for colonization, not an icy wilderness. The extreme storms, formidable icebergs, and unimaginable cold of the Southern Ocean acted as a natural barrier, pushing back even the most intrepid sailors. The true age of Antarctic exploration, however, began in the late 1700s, driven by scientific curiosity, the promise of rich sealing and whaling grounds, and national prestige. These first brave humans faced conditions of unparalleled severity, pushing the limits of human endurance and the capabilities of their wooden ships, slowly unveiling the secrets of the world's coldest continent. One of the most significant figures in the early push towards Antarctica was Captain James Cook, a British navigator whose voyages in the 1770s forever changed the map of the world. On his second circumnavigation of the globe between 1772 and 1775, Cook was specifically tasked with finding or disproving the existence of the Great Southern Continent. He was the first to deliberately sail south of the Antarctic Circle, crossing it on January 17, 1773. His ships, Resolution and Adventure, navigated through treacherous pack ice and enormous icebergs, enduring fierce storms and biting cold. Cook circumnavigated the globe at high southern latitudes, reaching as far south as 71 degrees 10 minutes south latitude. While he did not sight the Antarctic mainland, he made it clear in his reports that if a continent existed, it was so deeply frozen as to be uninhabitable and of no practical use for human settlement. His meticulous charts and observations of the ice formations, weather patterns, and the sheer scale of the southern polar region were invaluable. Cook's voyages effectively removed the mythical Terra Australis from habitable zones, paving the way for future explorers to seek a truly polar continent. His challenges were immense: primitive navigation tools, wooden ships vulnerable to ice, the constant threat of scurvy among his crew, and the sheer psychological toll of months spent in a hostile, unmapped ocean. He demonstrated remarkable resilience and scientific rigour, setting a high standard for subsequent exploration. Following Cook's pioneering efforts, the early 1800s saw a surge of activity in the Southern Ocean, largely driven by the lucrative sealing industry. hunters from Britain and the United States ventured south in search of new hunting grounds for fur seals and elephant seals, whose pelts and oil were highly prized. It was during this period that the first confirmed sightings of land within the Antarctic region occurred. 3 individuals are often credited, and sometimes debated, with these initial sightings, all occurring around 1820. Reportedly sighted an ice-covered coastline, which is widely considered to be the first undisputed sighting of the Antarctic mainland, specifically the Fimbul ice shelf. Bellinghausen's expedition had been dispatched by Tsar Alexander I with the explicit goal of exploring the southern polar regions and finding the unknown southern continent. His logs detailed encounters with dense pack ice and ice formations. Just days later, on January 30, 1820, Edward Bransfield, a British Royal Navy officer surveying the South Shetland Islands, sighted the northern tip of the Antarctic Peninsula, naming it Trinity Land. Bransfield's mission was to chart the newly discovered South Shetland Islands, which were already a hotbed of sealing activity. Simultaneously, in November 1820, Nathaniel Palmer, an American sealer, also sighted the Antarctic Peninsula while exploring for new sealing grounds. The exact order of these sightings and which individual deserves ultimate credit remains a point of historical discussion, but collectively, these voyages mark the definitive discovery of the Antarctic landmass. Their discoveries were not merely geographical, they revealed a land of ice, devoid of the temperate lands previously imagined. The challenges for these sealers and naval explorers were basic survival, navigating treacherous waters without accurate charts, avoiding collision with massive icebergs, and protecting their ships from the relentless pressure of pack ice. Scurvy remained a constant threat, as did the sheer isolation from any form of rescue. The mid to late 1800s saw several national expeditions, though significant inland exploration remained elusive. These expeditions, often driven by scientific goals and national pride, aimed to penetrate the ice barrier further. The British Antarctic expedition of 1839 to 1843, led by James Clark Ross, made significant advances. Ross, in command of HMS Erebus and HMS Terror, navigated the sea that now bears his name, discovering the Ross Ice Shelf, a formidable barrier of ice hundreds of meters high, which he initially named the Great Ice Barrier. He also discovered and named Mount Erebus, an active volcano, and Mount Terror. Ross pushed further south than anyone before him, reaching 78 degrees south latitude. His expedition made important magnetic, meteorological, and oceanographic observations, contributing greatly to the understanding of the continent's surrounding environment. However, the impenetrable ice shelf prevented any significant landing on the mainland beyond the coast. Challenges for Ross included the immense scale of the ice shelf, the ferocity of Antarctic storms, and the struggle to push through constantly shifting pack ice. The dawn of the 20th century ushered in what is famously known as the heroic age of Antarctic exploration, a period spanning roughly from 1897 to 1917. This era was characterized by ambitious goals, primarily the race to reach the South Pole, but also by unprecedented scientific inquiry and remarkable feats of human endurance. The expeditions of this age involved overwintering on the continent, extensive sledge journeys, and pushing deep into the interior, often with tragic consequences. Carsten Borch-Grevink, a Norwegian explorer, led the Southern Cross expedition, the first to overwinter on the Antarctic mainland, from 1899 to 1900. His party established a hut at Cape Adare and spent a year conducting meteorological observations, magnetic surveys, and biological studies. They also made the first sledge journey on the mainland, albeit a short one. Their discoveries were modest, but the very act of overwintering proved it was possible, laying crucial groundwork for subsequent expeditions. The challenges they faced were profound: crude shelters, extreme isolation, the constant cold, and the psychological strain of living in perpetual darkness during the winter months. Scurvy was a persistent threat due to dietary deficiencies. Following Borch-Grevink, the British launched their first major scientific expedition of the heroic age, the Discovery Expedition, led by Robert Falcon Scott from 1901 to 1904. Scott, commanding the purpose-built research vessel Discovery, established a base at McMurdo Sound. This expedition significantly advanced scientific knowledge of Antarctica's geography, geology, biology, and meteorology. Scott, along with Ernest Shackleton and Edward Wilson, made a pioneering sledge journey south, reaching 82 degrees 17 minutes south latitude, the furthest south anyone had been at that time. They discovered King Edward VII Land and conducted extensive geological surveys of the Transantarctic Mountains, including the discovery of the Dry Valleys, a rare ice-free area. Their challenges were immense. They struggled with primitive sledging techniques, largely relying on man-hauling, which proved incredibly arduous and inefficient. Their dogs were poorly understood and ill-suited for the task. They grappled with unknown conditions, learning by painful trial and error about polar clothing, food, and transport. Scurvy and frostbite were constant companions. Despite the hardships, the scientific output was substantial, including extensive mapping and the collection of fossil evidence. Ernest Shackleton, a veteran of Scott's Discovery expedition, returned to Antarctica in 1907, leading his own Nimrod expedition, which lasted until 1909. Shackleton's primary goal was to be the first to reach the South Pole. His party established a base at Cape Royds on Ross Island. During this expedition, key scientific achievements were made, including the ascent of Mount Erebus, the discovery of its active volcanic crater, and the first geological party to reach the Beardmore Glacier, a massive ice stream providing a route up onto the polar plateau. A separate party, led by T.W. Edgeworth David, reached the South Magnetic Pole, marking a significant geographical achievement. Shackleton's main polar party, using ponies for hauling, made an incredible push south, eventually reaching 88 degrees 23 minutes south latitude, just 97 geographical miles from the pole, before turning back due to dwindling supplies and the deteriorating health of his men. His decision to turn back, famously stating, "A live donkey is better than a dead lion," saved his men's lives. The challenges were extreme cold, ferocious blizzards, limited food, and the realization that their reliance on ponies was flawed. Shackleton's leadership, resourcefulness, and ability to inspire loyalty in his men became legendary. The pinnacle of the race to the South Pole occurred between 1910 and 1912, involving two rival expeditions. Roald Amundsen, a Norwegian explorer, led the Fram expedition, utilizing his extensive experience in Arctic polar travel, particularly with dog teams and skiing. Amundsen established his base camp, Framheim, in the Bay of Whales, closer to the South Pole than Scott's base. His approach was meticulously planned and executed with remarkable efficiency. He established a series of supply depots along his route to the pole, ensuring his team would have sufficient food and fuel for the return journey. Amundsen's team, comprising 5 men and 52 dogs, set off for the pole on October 19, 1911. They covered the distance with surprising speed and relative ease due to their expert use of skis and their well-trained dog teams. They navigated the perilous Axel Heiberg Glacier, scaling the Transantarctic Mountains, and reached the South Pole on December 14, 1911, becoming the first humans to achieve this feat. Their challenges included the unseen dangers of crevasses, navigating through complex mountain terrain, and enduring extreme cold and high altitude on the polar plateau. Amundsen's success was largely attributed to his adoption of indigenous polar techniques, his strategic planning, and his understanding of how to work with dogs effectively in the cold. Simultaneously, Robert Falcon Scott returned to Antarctica with the Terra Nova expedition, also aiming for the South Pole. Scott's expedition was a broader scientific endeavour, carrying out extensive geological, biological and meteorological research. His polar journey began in November 1911. Scott relied on a mix of transport methods: motor sledges, ponies and man-hauling. Unfortunately, the motor sledges broke down early, and the ponies struggled in the extreme conditions, forcing the men to man-haul heavy sledges for much of the journey. Scott's 5-man polar party eventually reached the South Pole on January 17, 1912, only to find Amundsen's Norwegian flag and tent, confirming they had been beaten. The return journey for Scott's party became a tragic epic of endurance. They faced exceptionally severe weather, blizzards, dwindling supplies, and the onset of scurvy. One by one, the men succumbed to the harsh conditions, frostbite, exhaustion, and starvation. Edgar Evans died in February, Lawrence Oates famously walked out into a blizzard in March, and Scott, Edward Wilson, and Henry Bowers died in their tent in late March, just 11 miles from a critical supply depot. Their bodies were found 8 months later by a search party. Scott's expedition made valuable scientific discoveries before the polar journey, including geological samples containing Glossopterus fossils, proving Antarctica's ancient connection to other continents. Their immense suffering and ultimate sacrifice became a powerful narrative in the history of exploration. Douglas Mawson, an Australian geologist who had served on Shackleton's Nimrod expedition, led the Australasian Antarctic expedition from 1911 to 1914, focusing on scientific exploration of previously uncharted regions of East Antarctica. Mawson established his main base at Cape Denison, Commonwealth Bay, known as the home of the blizzard, due to its consistently high winds. His expedition was remarkably comprehensive in its scientific scope, deploying several parties to map and study vast areas. Mawson's personal ordeal on his Far Eastern Party sledge journey is one of the most harrowing tales in polar history. After his 2 companions perished, one falling into a crevasse and taking their supplies with him, and the other succumbing to illness and exhaustion, Mawson was left alone, hundreds of miles from base, battling starvation, frostbite, and deep despair. He survived by eating the expedition dogs and pushing through immense physical and psychological pain, eventually making it back to base barely alive. He was so late that the ship had left, and he and 6 others had to overwinter for a second year. Despite the personal tragedy, Mawson's expedition made an enormous scientific contribution, charting vast stretches of coastline, making significant meteorological observations, and gathering extensive geological and biological collections from a previously unknown part of the continent. His discoveries included evidence of past glaciation and detailed mapping of coastal areas. The final major expedition of the heroic age was Ernest Shackleton's Imperial Transantarctic Expedition from 1914 to 1916, which aimed to achieve the first land crossing of the continent. Shackleton's ship, the Endurance, became trapped and eventually crushed by pack ice in the Weddell Sea before the landing party could even set foot on the continent. What followed was an epic tale of survival. Shackleton and his 27 men endured months drifting on ice floes, eventually launching their lifeboats in search of land. Shackleton, along with 5 companions, undertook an 82-mile open boat journey in the 22.5-foot lifeboat James Caird across some of the world's most tempestuous seas to reach South Georgia, an island with a whaling station. Upon landing, they faced the unprecedented challenge of crossing South Georgia's mountainous, glaciated interior to reach help. Shackleton's remarkable leadership and navigation skills led to the successful rescue of all his men from Elephant Island, a small, desolate island where the rest of his party had been waiting for months. While the expedition failed in its primary goal of crossing the continent and made no new geographical discoveries of the Antarctic mainland, it stands as an unparalleled story of human resilience, courage, and leadership in the face of unimaginable adversity. The scientific records and photographs kept during the ordeal, though not about the continent itself, provided unique insights into the behaviour of sea ice and the psychological aspects of survival. The challenges faced by these early explorers were truly monumental, testing the very limits of human endurance and ingenuity. The extreme cold was a constant and deadly adversary. Temperatures plummeted to tens of degrees below 0 Celsius, and often much colder, leading to severe frostbite, hypothermia, and the freezing of equipment. Maintaining warmth was a perpetual struggle, relying on layers of wool and furs and basic stoves. Blizzards and storms swept across the continent with incredible ferocity, bringing whiteouts that disoriented even experienced navigators, making travel impossible and trapping parties for days or weeks. These storms posed significant risks of getting lost, falling into crevasses, or simply freezing to death. The unpredictable nature of the ice itself presented immense dangers. Sea ice could suddenly break up, stranding ships or sledge parties, while pressure ridges formed by ice movement could crush vessels or create impassable barriers. On land, hidden crevasses, vast cracks in the glaciers were a constant peril, swallowing men, dogs, and supplies without warning. Many lives were lost to these unseen traps. Navigation in such a featureless, vast and often cloudy environment was incredibly difficult. Compasses became unreliable closer to the magnetic poles, and the lack of distinct landmarks made precise positioning a challenge. The early explorers relied on sextants for celestial navigation, which required clear skies, a rarity in parts of Antarctica. Logistics and supplies were a continuous battle. Ships could only carry a finite amount of food, fuel and equipment, and resupply was impossible for months, sometimes years. The sheer weight of supplies needed for long sledge journeys meant difficult decisions had to be made about what to carry. Scurvy, a disease caused by vitamin C deficiency, plagued nearly every expedition, debilitating men and leading to deaths. Although the cause was eventually understood, fresh food was often impossible to obtain. The isolation of Antarctica was profound. For months on end, explorers were cut off from the rest of the world, with no means of communication or rescue. This extreme isolation, coupled with the perpetual darkness of winter, took a severe psychological toll, leading to depression and mental strain. The technological limitations of the era compounded these challenges. Primitive wooden ships, though robust for their time, were vulnerable to the crushing forces of pack ice. Communication was non-existent beyond flags or visual signals, making coordination difficult and immediate rescue impossible. Medical knowledge was rudimentary, and treatments for frostbite, snowblindness and scurvy were often ineffective. The explorers were often operating with a profound lack of knowledge about polar travel. They had to learn, often through painful experience, the most effective methods for building shelters, cooking in extreme cold, designing appropriate clothing, and handling animals like dogs and ponies in a polar environment. Many early attempts at motor transport failed spectacularly due to the cold and rugged terrain. Despite these overwhelming challenges, the early explorers pushed forward, driven by a spirit of adventure, scientific inquiry, and the desire to plant their national flag at the ends of the earth. Their initial discoveries, though hard-won, laid the foundation for all subsequent Antarctic research. They began the process of mapping the vast coastline and some of the interior features, correcting centuries of speculation. They identified major mountain ranges such as the Transantarctic Mountains, which traverse the continent. The discovery of active volcanoes like Mount Erebus provided insights into the continent's geological activity. Geological observations led to the collection of fossil evidence, crucially including plant fossils like Glossopteris, which provided undeniable proof that Antarctica was once part of the ancient supercontinent Gondwana and had a much warmer climate, supporting lush vegetation and diverse animal life. They also documented unique geological formations, such as the ice-free dry valleys. Early meteorological observations began to characterize the extreme weather patterns of the continent, including the ferocious katabatic winds. Zoological discoveries included new species of penguins, seals, and other marine life, providing initial insights into Antarctica's unique ecosystems. While their understanding of ice dynamics was rudimentary, their observations of ice shelves, glaciers, and sea ice provided the first empirical data on the continent's frozen mantle. These early efforts, born of immense courage and often tragic sacrifice, transformed Antarctica from a blank space on the map into a continent of profound scientific interest and enduring mystery, setting the stage for future generations to peel back its icy veil. The stories of these brave men endure, not just as tales of adventure, but as testaments to the human spirit's capacity to confront and overcome the most extreme environments on Earth. Beneath the colossal expanse of Antarctica's ice sheets lies a world entirely invisible from the surface, a continent of mountains, valleys, plains, and even liquid lakes. This hidden land, known as subglacial topography, is completely obscured by thousands of meters of solid ice, creating one of the Earth's most significant unexplored frontiers. The sheer volume of ice that covers Antarctica, averaging approximately 1.8 kilometers in thickness and reaching over 4.5 kilometers in some areas, acts as an impenetrable veil. Sunlight cannot penetrate these depths, and traditional methods of aerial photography or ground-based surveys are utterly useless in revealing what lies beneath. The ice itself is not merely a static cap. It is a dynamic, flowing mass that has been accumulating for tens of millions of years, slowly burying and preserving the ancient landscapes that existed before its formation. This profound burial has sealed away geological features and potentially unique ecosystems, creating a natural archive of Earth's past. Understanding this hidden land is not just a matter of geographical curiosity. It is fundamental to predicting the future behaviour of the ice sheet and its impact on global sea levels. The primary reason this land is hidden is the immense thickness and opacity of the ice. Unlike water, which can be seen through to varying depths, solid glacial ice is opaque to visible light beyond a few meters. This means that from above, all that is visible is an endless, undulating white landscape. The ice sheet formed over a prolonged period, starting approximately 34 million years ago, when Antarctica separated from other land masses, allowing the development of the Antarctic circumpolar current. This oceanic isolation led to a dramatic cooling of the continent, causing snow to fall and accumulate year after year without significant melting. As successive layers of snow were deposited, they compacted under their own weight, transforming into firn and then into dense glacial ice. This process gradually submerged entire mountain ranges, filled vast valleys, and covered existing river systems and plains. The pressure from the overlying ice is so enormous that it has even caused the underlying continental crust to depress, or sink, by hundreds of meters, making much of the land surface beneath the ice sheet lie below present-day sea level, even though Antarctica is a true continent, not just an archipelago of islands. Given that the land beneath the ice is invisible, how do scientists know what lies beneath? The answer lies in sophisticated geophysical techniques that can see through the ice. The most widely used and effective method is ice-penetrating radar, also known as radio echo sounding. This technology involves emitting radio waves from an aircraft flying over the ice surface or from ground-based vehicles. These radio waves travel through the ice until they encounter a boundary where the electrical properties change, such as the interface between the ice and the underlying bedrock, or the interface between ice and liquid water. At these boundaries, a portion of the radar signal is reflected back to the receiver. By measuring the time it takes for the radar waves to travel down to the bedrock and back, and knowing the speed of radio waves through ice, scientists can calculate the precise thickness of the ice, and, by subtraction from the surface elevation, determine the topography of the land beneath. The strength and characteristics of the reflected signal can also indicate whether the ice is frozen to the bedrock or if there is a layer of liquid water at the base. Airborne radar surveys have extensively mapped large parts of the continent, revealing the broad outlines of its hidden geography. While ice-penetrating radar provides excellent resolution for ice thickness and bedrock topography, other methods offer complementary information, particularly about the geology and composition of the subglacial landscape. Seismic surveys, for instance, use acoustic energy to probe deeper into the Earth. This involves generating vibrations, either by small explosions or specialized vibrator trucks on the ice surface. These seismic waves travel through the ice and the underlying bedrock, reflecting or refracting off different rock layers and geological structures. Receivers placed on the ice surface record these returning waves. By analyzing the arrival times and characteristics of these seismic waves, scientists can create detailed images of the rock layers, identify faults, and even detect the presence of liquid water or sediment layers at the ice bedrock interface. Seismic methods offer higher resolution than radar for specific geological features, but are more labour-intensive and thus used for targeted studies rather than continent-wide mapping. Gravity measurements provide another piece of the puzzle, revealing large-scale features of the subglacial landmass. Earth's gravitational field is not uniform. It varies slightly depending on the density of the underlying material. Denser rock creates a stronger gravitational pull than less dense materials like ice or water. By using highly sensitive instruments called gravimeters, mounted on aircraft or satellites, scientists can detect these tiny variations in gravity. From these measurements, broad outlines of geological features such as deep basins or massive mountain ranges can be inferred. For example, a region with a stronger gravitational pull might indicate a thicker crust or denser rocks beneath the ice. While gravity data does not provide the same level of detail as radar or seismic methods, It is invaluable for understanding the overall geological structure and tectonic framework of the continent hidden beneath its ice sheet. Magnetic surveys, conducted similarly from aircraft, measure variations in Earth's magnetic field caused by the presence of magnetic minerals in the underlying bedrock. These variations can help identify different rock types, ancient volcanic activity, and tectonic boundaries, providing further insights into the geological history of the continent. Through these sophisticated techniques, scientists have unveiled some truly remarkable hidden features. One of the most significant discoveries is the Gamburtsev Mountains, a vast, rugged mountain range completely buried beneath the East Antarctic ice sheet. These mountains, comparable in scale to the European Alps, with peaks reaching over 3,000 meters, or nearly 10,000 feet, and valleys over 1,000 meters deep, were first hinted at by Soviet expeditions in the 1950s, but were only extensively mapped and fully characterized in the early 21st century using advanced radar surveys. The existence of such a prominent mountain range beneath kilometers of ice was a profound surprise. Their significance lies in their potential role in the initiation and growth of the East Antarctic ice sheet. It is thought that the high peaks acted as nucleation points for ice accumulation, allowing glaciers to form and eventually coalesce into the massive ice sheet we see today. The mountains also influence modern ice flow, acting as barriers or guiding channels for the slow movement of ice across the continent. Perhaps even more astonishing than hidden mountains is the discovery of vast subglacial lakes. The concept of liquid water existing beneath kilometers of ice seemed paradoxical at first, but scientific evidence, primarily from radar and seismic surveys, has confirmed the existence of hundreds of these hidden bodies of water. The most famous and largest is Lake Vostok, discovered by Russian and British scientists in the 1970s and 80s, lying beneath nearly 4 kilometers of ice in East Antarctica. Lake Vostok is enormous, comparable in size to North America's Lake Ontario, stretching for approximately 250 kilometers long and 50 kilometers wide. It has been isolated from the Earth's atmosphere for an estimated 15 million years. The lake remains liquid due to a combination of factors. Geothermal heat from Earth's interior warms the bedrock beneath the ice, and the immense pressure exerted by the overlying ice lowers the melting point of water, allowing it to remain liquid even at temperatures slightly below 0 degrees Celsius. The thick ice sheet above also acts as an incredible insulator, trapping any heat that rises from below. The discovery of Lake Vostok and subsequently hundreds of other subglacial lakes across the continent has opened up entirely new fields of research. These lakes are pristine, isolated environments, potentially harboring unique microbial life forms that have evolved in complete darkness, under high pressure, and with very limited energy sources. The potential for discovering novel biochemical pathways and even new branches on the tree of life within these hidden aquatic ecosystems is immense. Scientists are also exploring whether these lakes are interconnected by subglacial rivers, forming a vast hydrological network beneath the ice. The implications for astrobiology are profound, as these subglacial lakes on Earth serve as natural analogues for potential life on icy moons in our solar system, such as Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, which are thought to harbour subsurface oceans. The challenges of exploring these lakes are significant, requiring ultra-clean drilling techniques to avoid contaminating these pristine environments. Beyond mountains and lakes, the hidden lands of Antarctica also feature extensive subglacial valleys and canyons. These are deep troughs carved either by ancient rivers and glaciers before the continent became glaciated, or by the powerful flow of subglacial meltwater today. Some of these valleys are immense, such as the enormous canyons discovered beneath the Aurora Basin in East Antarctica, which could channel significant amounts of ice towards the coast. These valleys play a critical role in ice sheet dynamics, often acting as pathways for fast-flowing ice streams, which are like rivers of ice moving more rapidly than the surrounding ice sheet. Understanding the morphology and orientation of these hidden valleys is crucial for predicting how the ice sheet will respond to future climate warming, as they can accelerate the discharge of ice into the ocean. Detailed mapping has also revealed complex continental divides and basins, outlining the true shape of the Antarctic landmass beneath its icy shroud. The West Antarctic Rift System, a major tectonic feature, is largely hidden beneath the ice. indicating active geological processes occurring beneath the frozen surface. The implications of these hidden lands are far-reaching. Firstly, they are critical for understanding ice sheet dynamics. The topography of the bedrock beneath the ice directly influences how the ice flows. Rugged, mountainous terrain can pin the ice, slowing its movement, while smooth, gently sloping bedrock or the presence of basal water can allow the ice to flow much faster. Subglacial valleys can channel fast-flowing ice streams, which are the primary conduits for ice discharge from the interior to the ocean. The presence of liquid water at the base of the ice sheet acts as a lubricant, reducing friction and allowing the ice to slide more rapidly. Accurate maps of this subglacial topography are therefore essential for building more precise models of ice sheet behaviour and predicting its contribution to future global sea level rise. Without knowing the shape of the land beneath, predictions of ice sheet stability and melt rates would be highly inaccurate. Secondly, the hidden lands provide invaluable insights into Antarctica's past climate and geology. The preserved landscapes beneath the ice offer a unique window into what Antarctica looked like before it became glaciated. Discoveries of ancient river systems and lake beds reveal a much warmer, wetter past. The geological features such as hidden mountain ranges and rift systems inform our understanding of plate tectonics and the continent's deep geological history. The identification of subglacial volcanoes and areas of high geothermal heat flow helps explain the presence of subglacial lakes and influences ice dynamics in specific regions. These discoveries challenge the long-held notion of Antarctica as a static, perpetually frozen continent, revealing a dynamic geological past that continues to influence its present-day behaviour. Thirdly, the biological and astrobiological implications of subglacial environments are profound. The isolation of subglacial lakes, like Lake Vostok, raises the possibility of discovering unique microbial ecosystems that have evolved entirely independently from surface life for millions of years. These organisms would represent extremophiles, adapted to conditions of perpetual darkness, high pressure, limited nutrients, and potentially unique chemical compositions. Studying them could provide insights into the very limits of life's adaptability and offer clues about the potential for life in similar extreme environments elsewhere in the universe, such as subsurface oceans on icy moons. The very existence of these hidden habitats expands our understanding of where life can thrive. Finally, accurate knowledge of the hidden lands is crucial for predicting future sea level rise. The stability of the ice sheets, particularly the West Antarctic ice sheet, is highly dependent on the topography of the bedrock upon which they rest. Many parts of the West Antarctic ice sheet are grounded below sea level, meaning that as warmer ocean water encroaches, it can melt the ice from below, causing the grounding line, the point where the ice leaves the bedrock and begins to float, to retreat. If the bedrock slopes downwards towards the continent's interior, this retreat can become unstable and irreversible, leading to rapid ice loss. Understanding the precise shape of these subglacial basins and troughs is therefore vital for forecasting the rate and extent of ice sheet collapse and its contribution to global sea levels. The challenges of studying these hidden lands remain formidable. The extreme remoteness, the harsh environmental conditions, and the logistical difficulties of operating scientific equipment in such a place make fieldwork incredibly challenging and expensive. Despite these hurdles, advancements in technology continue to peel back the icy veil, revealing more and more of the secret continent that lies beneath Antarctica's frozen deep, a landscape that holds keys to Earth's past, present, and future. The Antarctic ice sheet, a truly colossal mass of frozen water, is not a static feature but a dynamic system constantly in motion. Its movement, often imperceptible to the human eye over short periods, involves powerful forces that continuously reshape the continent and dictate what remains buried beneath its enormous weight. The primary mechanisms governing how glacial ice moves are internal deformation, also known as creep, and basal sliding. Internal deformation occurs when the ice itself deforms under its own immense weight, acting like a very slow-moving, viscous fluid. The ice crystals within the glacier are not rigidly fixed, but can slide past one another along their crystal planes, and individual water molecules can rearrange. This process is more pronounced at greater depths within the ice sheet, where the pressure is highest and where the ice temperature might be closer to its melting point. The ice at the bottom layers, being warmer and under more pressure, flows more readily than the colder brittle ice near the surface. This continuous internal deformation means that even if the base of the glacier were frozen solid to the bedrock, the ice would still flow due to stresses within the ice mass itself. The rate of internal deformation is influenced by the ice temperature. Warmer ice, even if below freezing, deforms more easily than colder ice. This is a key reason why ice flow is faster in temperate glaciers compared to polar glaciers, though in Antarctica, the sheer thickness compensates for the extreme cold, allowing significant internal deformation. Basal sliding is the second major mechanism of ice movement, and often contributes significantly to rapid ice flow. This occurs when the bottom of the glacier or ice sheet slides over its underlying bedrock. For basal sliding to happen, there must be a thin layer of liquid water between the ice and the rock. This basal meltwater acts as a lubricant, reducing friction and allowing the immense ice mass to move more easily. This meltwater can be generated by several factors. Pressure melting, where the enormous weight of the overlying ice lowers the melting point of water, causing ice at the base to melt even if its temperature is below 0 degrees Celsius. Frictional heat generated by the movement of ice over the bedrock, and geothermal heat flux, which is the heat rising from Earth's interior. In many parts of Antarctica, especially beneath the fast-flowing ice streams, the presence of basal meltwater is crucial for enabling rapid movement. The amount of basal meltwater can vary seasonally or spatially, influencing the speed of ice flow. If the ice is frozen to the bedrock, basal sliding cannot occur, and ice movement is solely dependent on internal deformation, which is generally slower. The interaction between the ice and the underlying bedrock, whether it is frozen or lubricated by meltwater, is a critical factor determining the velocity of the ice flow. A third, often overlooked mechanism contributing to ice flow is the deformation of subglacial till. Till is a mixture of sediment and rock debris that lies between the ice and the bedrock. If this till is saturated with water, it can become deformable, acting like a soft, squishy layer that allows the overlying ice to slide over it. This phenomenon, known as subglacial till deformation, can account for a substantial portion of the total ice movement, particularly in regions where the bedrock is soft or unconsolidated, or where large amounts of meltwater are present. The degree to which subglacial till deforms depends on its composition, water content, and the pressure exerted by the ice. In some fast-flowing ice streams, it is believed that the deformation of a thick layer of water, saturated till, is the dominant mechanism driving rapid ice movement. The presence of a deformable bed can lead to very high velocities, much greater than those achieved through internal deformation, or even simple basal sliding over hard rock. Understanding the properties of subglacial till and its interaction with meltwater is vital for accurately modelling ice flow and predicting the behaviour of ice sheets. Several factors collectively influence the rate and style of ice flow across Antarctica. Ice thickness is a primary driver. Thicker ice exerts greater pressure on its base, leading to faster internal deformation and potentially more pressure melting for basal sliding. The slope of the underlying bedrock also plays a crucial role. Ice flows downhill under gravity, so steeper slopes generally result in faster flow. The temperature of the ice, as mentioned, affects its deformability. Warmer ice moves more readily. The presence of liquid water at the base, whether from pressure melting, frictional heat, or geothermal flux, significantly lubricates the ice, increasing basal sliding rates. The roughness of the bedrock too matters. A smoother bed allows for easier sliding compared to a rough, irregular surface that creates more friction. The overall geometry of the ice sheet, including its surface slope and the presence of confining valleys or open plains, also directs and shapes the flow patterns. All these factors interact in complex ways, making ice dynamics a challenging but fascinating area of study. The massive Antarctic ice sheet is not a single, uniform block, but a complex system of interconnected flow regimes. The largest scale of flow is the ice sheet itself, covering the entire continent. Within the ice sheet, there are distinct types of flow. Outlet glaciers are narrower, faster-moving streams of ice that drain large areas of the ice sheet through valleys or gaps in coastal mountain ranges, discharging ice directly into the ocean. Ice streams are vast, fast-flowing rivers of ice, tens to hundreds of kilometers wide and hundreds of kilometers long that move much more rapidly than the surrounding slower-moving ice sheet. They channel immense volumes of ice from the interior to the coast, acting as major arteries for ice discharge. These ice streams are often lubricated by basal meltwater or deformable subglacial till and can reach speeds of several hundred meters per year, whereas the interior ice might move only a few meters per year. Ice shelves are large, floating platforms of ice that extend from the land-based ice sheet into the ocean. They are fed by glaciers and ice streams flowing from the continent. While floating, they do not directly contribute to sea level rise when they melt or carve icebergs, because they are already displacing ocean water. However, they play a crucial role by acting as a buttress, effectively holding back the flow of land-based ice behind them. The buttressing effect of ice shelves is fundamental to the stability of the Antarctic ice sheet. By impeding the flow of glaciers and ice streams, they reduce the rate at which land-based ice enters the ocean. When an ice shelf collapses or significantly thins, this buttressing effect is weakened or lost, causing the ice streams and glaciers behind it to accelerate their flow towards the sea. This acceleration directly contributes to global sea level rise. Recent decades have seen the dramatic collapse of several ice shelves on the Antarctic peninsula, such as the Larsen A and Larsen B ice shelves, following periods of atmospheric and oceanic warming. These collapses were followed by a significant acceleration of the glaciers that fed them, highlighting the critical role ice shelves play in regulating ice discharge. The integrity of ice shelves is thus a key indicator of the health of the entire ice sheet system. Warming ocean waters, particularly those circulating beneath the floating ice shelves, are a major driver of ice shelf thinning and retreat. This subsurface melting can occur even in very cold regions, as ocean currents bring relatively warmer water into contact with the ice. The mass balance of the Antarctic ice sheet refers to the difference between the ice gained through snowfall and the ice lost through melting and iceberg calving. Accumulation, primarily in the form of snowfall, adds mass to the ice sheet. Ablation, or ice loss, occurs through various processes. Surface melting, though relatively minor in most of Antarctica due to consistently low temperatures, can occur in warmer coastal areas and on ice shelves. Basal melting, as discussed, happens at the interface between the ice and the bedrock or ocean, often lubricated by geothermal heat or warmer ocean waters. The most significant form of mass loss for the Antarctic ice sheet is iceberg calving, where large chunks of ice break off from the edges of glaciers and ice shelves and fall into the ocean. These icebergs can be enormous, some larger than small countries, and their detachment represents a direct loss of mass from the ice sheet system. A negative mass balance, where ice loss exceeds ice gain, indicates that the ice sheet is shrinking and contributing to sea level rise. A positive mass balance indicates growth. Satellite measurements, including gravimetry and altimetry, are crucial tools for monitoring these mass balance changes across the entire continent with high precision, providing direct evidence of whether Antarctica is gaining or losing ice. Geothermal heat flux, the flow of heat from Earth's interior, also plays a subtle yet important role in ice dynamics. While not the primary driver of melt, it provides a constant source of heat at the base of the ice sheet. In areas where geothermal heat flux is particularly high, for example, near subglacial volcanoes or rift systems, it can contribute significantly to basal melting and the formation of subglacial lakes. This basal water can then lubricate the ice, influencing its flow speed. Even in areas with average geothermal heat flux, this heat can be sufficient to raise the temperature of the ice at its base close to the pressure melting point, facilitating basal sliding. Understanding the spatial variations in geothermal heat flux across Antarctica is important for accurately modelling basal conditions and predicting ice flow. Specialised drilling operations can measure temperature gradients within the ice and bedrock, providing direct data on heat flow from the Earth's interior. Climate change is profoundly impacting Antarctic ice dynamics, leading to significant changes in ice flow and mass balance. Rising global temperatures, primarily driven by human activities, are causing both atmospheric and oceanic warming around Antarctica. Atmospheric warming is particularly noticeable on the Antarctic peninsula, leading to increased surface melt and ice shelf collapse. However, the most significant threat to the larger East and West Antarctic ice sheets comes from warming ocean waters. These warmer currents circulate beneath the floating ice shelves, melting the ice from below at the grounding lines where the ice transitions from resting on bedrock to floating. This basal melting can thin ice shelves and cause the grounding line to retreat, destabilizing the ice sheet behind it. As grounding lines retreat into deeper, downward-sloping bedrock, the process can become self-perpetuating and lead to rapid ice loss, a phenomenon known as marine ice sheet instability. The acceleration of ice streams and glaciers, driven by weakened buttressing from ice shelves and increased basal lubrication, is a direct consequence of these warming trends. The combined effect of increased melt and accelerated flow contributes directly and increasingly to global sea level rise. The powerful forces of ice dynamics continuously reshape the Antarctic continent, both visibly and invisibly. Glacial erosion is a key process. As the ice flows over the land, it acts like a giant abrasive belt, grinding down rocks and carving out distinctive landforms. Plucking occurs when the ice freezes onto rocks and then pulls them away as the glacier moves. Abrasion involves the scraping action of rock debris embedded within the flowing ice, smoothing and polishing bedrock surfaces. These erosive processes sculpt deep U-shaped valleys, dramatic fjords along the coast, and bowl-shaped cirques in mountainous regions. The sheer scale of the Antarctic ice sheet means it has overridden and sculpted an entire continent, burying mountains and creating vast subglacial plains. Material eroded by the ice is transported and deposited as glacial till, forming features like moraines at the ice margins or drumlins beneath the ice. The flow of ice can also create subglacial troughs and channels, which become pathways for faster ice movement. These powerful forces dictate the shape of the subglacial landscape and significantly influence what features remain buried or are eventually exhumed by ice flow. The influence of ice dynamics on what remains buried beneath the ice is twofold. In areas where ice flow is very slow, particularly in the interior of the East Antarctic ice sheet, the ice acts as an excellent preserving medium. Here, ancient landscapes, geological features, and possibly even organic matter can remain undisturbed and protected for millions of years. The slow movement means minimal erosion, or deformation, of the underlying features. The ice effectively acts as a geological time capsule. However, in regions of faster ice flow, particularly in ice streams and outlet glaciers, the dynamic forces can actually exhume buried materials. The powerful erosive action can remove overlying ice and bedrock, bringing ancient rock formations or even fossilized materials closer to the surface, or exposing them in nunataks, which are mountain peaks that protrude through the ice. Conversely, in areas of convergence or slowing ice, the ice can deposit large amounts of debris, further burying features. The continuous interaction between the moving ice and the underlying bedrock is thus a dynamic process of burial, preservation, erosion, and sometimes exhumation, constantly shaping the hidden world beneath Antarctica's frozen surface. Scientists employ a range of sophisticated measurement techniques to monitor and understand ice dynamics. Satellite altimetry uses laser or radar pulses from satellites to measure the precise elevation of the ice surface over time. Repeated measurements reveal changes in ice sheet thickness, indicating whether the ice is thinning or thickening, and thus whether it is losing or gaining mass. Satellite gravimetry, such as that provided by the Grace and Grace follow-on missions, measures tiny variations in Earth's gravitational field, caused by changes in the mass of the ice sheet. A decrease in gravitational pull over Antarctica indicates a loss of ice mass. Both altimetry and gravimetry provide large-scale, continent-wide assessments of mass balance. Global Positioning System receivers, or GPS units, placed directly on the ice surface, or on bedrock exposures around the ice sheet, can precisely track horizontal and vertical movements of the ice or land. These provide direct measurements of ice velocity and bedrock uplift or subsidence. Ice-penetrating radar, as previously mentioned, is crucial for mapping the thickness of the ice and the topography of the bedrock beneath it. By understanding the shape of the underlying land, scientists can better predict how the ice will flow and where potential areas of instability might exist. Seismic surveys, which use sound waves to image the subsurface, provide detailed information about the geological structure of the bedrock and the presence of liquid water or deformable sediments at the base of the ice. These techniques combined allow researchers to build increasingly accurate three-dimensional models of the ice sheet and its underlying environment, leading to a more comprehensive understanding of its dynamics. The continuous monitoring and research into ice dynamics are critical for refining projections of future sea level rise and for developing strategies to mitigate the impacts of a changing climate. The slow but immense power of ice flow is a fundamental force shaping one of the Earth's most significant and mysterious continents. The frigid, often dark waters surrounding and beneath Antarctica are home to a remarkable group of fish, collectively known as ice fish. These creatures represent some of the most extraordinary examples of adaptation to extreme cold found anywhere on Earth. Their environment is characterized by consistently low temperatures, often hovering around -1.9 degrees Celsius or 28.6 degrees Fahrenheit, the freezing point of seawater. This extreme cold poses a severe challenge to most biological systems, as ice formation within cells is lethal. Yet these fish not only survive but thrive in these conditions, having evolved a suite of unique physiological and biochemical adaptations over millions of years. Their story is one of evolutionary triumph in one of the planet's most unforgiving environments. The dominant group of fish in these waters are the notothenioids, which comprise over 100 species and account for more than 90% of the fish biomass on the Antarctic continental shelf. Within this diverse group are the truly unique white-blooded icefish, belonging to the family Channictiidae, whose adaptations push the boundaries of biological possibility. One of the most critical adaptations for survival in sub-zero waters is the presence of antifreeze proteins, often referred to as antifreeze glycoproteins, or AFGPs. These proteins circulate in the blood and other bodily fluids of Antarctic fish and prevent ice crystals from forming and growing within their tissues. When a microscopic ice crystal enters the fish's body, these AFGPs bind to its surface, effectively inhibiting its growth and preventing it from becoming a larger, damaging crystal that would puncture cell membranes. They work by lowering the freezing point of the fish's body fluids below that of the surrounding seawater, without significantly altering the colligative properties like osmotic pressure. This non-colligative freezing point depression is crucial for preventing the fish from literally freezing solid. Different types of AFGPs have evolved in various fish species, but they all share the common function of ice inhibition. The evolution of these antifreeze proteins is considered a key event that allowed notothenioids to diversify and dominate the Antarctic ecosystem, as the continent cooled and glaciated millions of years ago. Without this adaptation, life in such persistently cold, ice-laden waters would be impossible for fish. Perhaps the most astonishing adaptation found in some ice fish is the complete absence of hemoglobin and red blood cells. These are the white-blooded ice fish, belonging to the family Channictiidae, of which there are 16 known species. Hemoglobin is the protein responsible for transporting oxygen in the blood of most vertebrates, giving blood its red colour. Without it, the blood of these ice fish is clear or milky white. This unique trait is a result of a genetic mutation that occurred millions of years ago, leading to the loss of functional hemoglobin genes. At first glance, this might seem like a severe disadvantage, as oxygen transport would be severely compromised. However, in the extremely cold waters of the Antarctic, oxygen is much more soluble than in warmer waters, meaning there is a relatively high concentration of dissolved oxygen available. These white-blooded ice fish compensate for the lack of hemoglobin by having significantly larger hearts and a much higher blood volume compared to red-blooded fish of similar size. Their blood vessels are also generally wider. This allows them to circulate a greater volume of oxygen-rich plasma, the liquid component of blood, to their tissues. Oxygen simply dissolves directly into the plasma and is transported. Their metabolic rates are also inherently low, meaning their oxygen demand is less than fish in warmer waters. This remarkable adaptation is a trade-off. While it allows them to thrive in superoxygenated cold water, it likely restricts them to this environment, as they would struggle to meet oxygen demands in warmer, less oxygen-rich waters. Even for the red-blooded notothenioids that do possess hemoglobin, there are adaptations related to oxygen transport. Their hemoglobin often has a higher affinity for oxygen at low temperatures, meaning it can efficiently pick up and release oxygen even in cold conditions. Their blood also typically has a higher viscosity due to the cold and the structure of their red blood cells. To compensate for this, they also tend to have larger hearts and higher blood volumes than their temperate counterparts, ensuring adequate circulation of oxygen to their tissues. Their metabolism is generally slower than fish in warmer climates, which reduces their overall oxygen demand, aligning with the slower pace of life dictated by the cold environment. This lowered metabolic rate is a common feature across many Antarctic organisms, reflecting the energetic challenges of living in extreme cold, where biochemical reactions naturally proceed at a slower pace. Another crucial physiological adaptation for ice fish involves the fluidity of their cell membranes. In cold temperatures, the fatty acids in cell membranes can become stiff and rigid, impairing vital cellular functions. Antarctic fish have evolved specialized lipids in their cell membranes, particularly unsaturated fatty acids, which remain fluid and flexible even at sub-zero temperatures. This allows their cells to maintain proper function, ensuring that enzymes can interact with substrates and that ion channels and transporters can operate efficiently. Without fluid membranes, cellular processes would grind to a halt, leading to cell death. This intricate biochemical fine-tuning at the molecular level is fundamental to their survival. Furthermore, the enzymes within their cells are adapted to function optimally at low temperatures. Enzymes from warm-adapted organisms would become inefficient or even denatured in the extreme cold. Icefish possess cold-adapted enzymes that maintain their structural integrity and catalytic activity under frigid conditions, ensuring that all metabolic pathways, from energy production to protein synthesis, can proceed effectively. Buoyancy control presents another challenge in cold water, as a swim bladder, typically used for buoyancy in most fish, requires a constant supply of gas, which is energetically costly to regulate in cold, high-pressure environments. Many Antarctic fish, particularly the notothenioids, have reduced or completely lost their swim bladders. Instead, they achieve neutral buoyancy through alternative strategies. Some species reduce the density of their bodies by accumulating large amounts of lipids, or fats, in their tissues and bones, which are less dense than water. Others have reduced bone density or cartilaginous skeletons, making them naturally lighter. This allows them to maintain their position in the water column with minimal energy expenditure, which is crucial in an energy-limited environment. For instance, the Antarctic silverfish, a key prey species, has a high lipid content that helps it remain buoyant in the water column, allowing it to move freely between the water and the underside of sea ice. The loss of a swim bladder is another example of an evolutionary trade-off, simplifying one physiological challenge while potentially restricting movement or habitat. The reproductive strategies of Antarctic fish are also tailored to their extreme environment. They generally exhibit slow growth rates and reach sexual maturity at a later age compared to fish in warmer waters. This reflects the slower metabolic rates and the limited food resources in their habitat. Many species also engage in parental care, with males guarding nests of eggs. This strategy, while requiring a significant energy investment from the parent, increases the survival rate of offspring in a harsh and predator-rich environment. For example, some Antarctic cod species lay large eggs, and the males guard them for extended periods, sometimes for several months, until hatching. This extended parental investment helps ensure the survival of their relatively few offspring, a common strategy in stable but resource-constrained environments where survival rates are otherwise low. The entire life cycle, from larval development to adult size, often takes many years, contributing to their generally long lifespans compared to fish in more temperate zones. Sensory adaptations are also crucial for survival in the often dark, deep waters of the Southern Ocean. While not unique to Antarctic fish, many species possess large eyes to maximize light capture in low-light conditions, particularly those living in deeper waters or under thick ice where light penetration is minimal. Others rely more on non-visual senses such as their lateral line system, which detects vibrations and pressure changes in the water, allowing them to navigate, find prey, and avoid predators in the absence of light. Some deep water species may also exhibit bioluminescence, the ability to produce light for communication or attracting prey. The precise adaptations vary depending on the specific habitat of the fish, whether it lives in the pelagic zone, the open water column, or on the benthic zone, the seafloor. The primary habitat for these unique fish is the Southern Ocean. The the cold, nutrient-rich waters that surround the Antarctic continent. Within this vast ocean, they occupy a range of niches. Many notothenioids are demersal, meaning they live on or near the seafloor, particularly on the continental shelf around Antarctica. Here they feed on benthic invertebrates, such as crustaceans, worms and mollusks. Others are pelagic, living in the open water column, feeding on krill, copepods and other small crustaceans, forming a crucial link in the Antarctic food web. Some species are adapted to live in close association with sea ice, using the ice underside for shelter and feeding on ice algae. The depth range can vary significantly, from shallow coastal waters to the abyssal plains of deep ocean trenches. The specialized nature of their adaptations means they are largely restricted to these frigid waters. They cannot survive in warmer ocean environments. This makes them highly endemic to the Antarctic region. Key species and families within the icefish group include the dominant notothenioids, which represent an adaptive radiation, meaning they evolved from a common ancestor to fill a wide array of ecological niches in the Antarctic. This group includes the Antarctic cod, such as Notothenia rossi and Disosticus morsoni, which are commercially important species and often found on the continental shelf. These are red-blooded fish that possess antifreeze proteins. The white-blooded icefish of the family Channictidae are another iconic group. These fish are instantly recognizable by their pale gills, which reflect their lack of red blood cells and hemoglobin. Examples include Chainocephalus aceratus and Chionodraco rastrospinosus. Other notable notothenioids include the Antarctic silverfish, Pleurogramma antarcticum, a small pelagic species that is a key prey item for seals, penguins and whales. The unique physiological characteristics of these fish groups make them focal points for scientific research, offering insights into extreme biology and evolutionary processes. Ecologically, Antarctic fish play a vital role in the Southern Ocean food web. Many species, particularly the Antarctic silverfish, serve as a critical link between the primary producers and smaller consumers like krill and the higher predators such as seals, penguins, and whales. They are prey for a wide array of marine mammals and seabirds, transferring energy up the food chain. Other species are important predators of smaller invertebrates or other fish, helping to regulate population sizes within their ecosystems. Their relatively slow growth and reproductive rates make their populations particularly vulnerable to overfishing, and careful management is essential to ensure their long-term sustainability. Their adaptations to cold also make them slow to recover from environmental disturbances, highlighting their fragility in a rapidly changing world. The impact of climate change poses significant threats to these highly specialized fish. Warming ocean waters, even slight increases in temperature, can stress these cold, adapted organisms whose physiological systems are tuned to extremely narrow temperature ranges. While they can produce antifreeze proteins to prevent freezing, their upper thermal limits are very low. Even a few degrees Celsius increase could push them beyond their thermal tolerance. Ocean acidification, caused by the absorption of excess carbon dioxide from the atmosphere into the oceans, is another serious threat. The increased acidity can impair the ability of fish to maintain their acid-base balance, affecting their metabolic processes, growth, and reproduction. It can also impact their prey species, such as krill, whose shell formation is sensitive to acidity. Furthermore, changes in sea ice extent and krill populations, both influenced by climate change, can disrupt the food sources and habitats of many Antarctic fish, potentially leading to declines in their populations. The discovery and research into icefish have a rich history. Early expeditions to Antarctica during the heroic age of exploration collected initial specimens, providing the first glimpses of the unique marine fauna of the region. However, it was primarily in the mid to late 20th century, with the advent of dedicated oceanographic research vessels and sophisticated sampling equipment, that scientists began to fully appreciate the remarkable adaptations of these fish. Breakthroughs in molecular biology and genetic sequencing in the late 20th and early 21st centuries allowed researchers to identify and characterize the specific antifreeze proteins and to understand the genetic basis for the loss of hemoglobin in white-blooded icefish. Modern research involves expeditions to collect live specimens for laboratory studies, utilizing specialized aquariums that can replicate the frigid Antarctic conditions. Scientists also deploy advanced instruments in the field, such as remotely operated vehicles and autonomous underwater vehicles, to observe fish in their natural habitats under the ice and in deep waters. The challenges of studying these fish are considerable, including the extreme logistical difficulties and costs of conducting research in Antarctica, the deep and treacherous waters they inhabit, and the need for specialized equipment to maintain their delicate physiological balance during collection and transport. Despite these hurdles, ongoing research continues to unveil new insights into the extraordinary biology of Antarctic icefish, offering vital lessons about life's resilience and the impacts of environmental change on highly adapted species. Their existence is a testament to the incredible power of evolution to shape life in the most extreme corners of our planet. The deep ocean trenches and abyssal plains near Antarctica represent one of Earth's most extreme and least explored environments, a realm of perpetual darkness, immense pressure, and chilling cold. Here, far removed from the sunlit surface waters, life has evolved in bizarre and resilient forms, pushing the boundaries of biological adaptation. This deep-sea world encompasses the continental slope, where the seabed plunges steeply from the shelf, the abyssal plains, vast flat areas stretching across the ocean floor at depths typically ranging from 3,000 to 6,000 meters, or about 10,000 to 20,000 feet, and the even deeper ocean trenches, which can descend beyond 10,000 meters, or 33,000 feet. In the Antarctic context, the Southern Ocean, with its unique current systems and immense ice coverage, adds further layers of complexity to these deep water habitats. The cold surface waters of the Southern Ocean sink, contributing to the formation of deep water masses that circulate globally, making even the deep sea here exceptionally cold, often close to 0 degrees Celsius or even slightly below, due to the influence of melting ice. The fundamental challenge for life in the deep sea is the absence of sunlight. Photosynthesis, the basis of most life on Earth, is impossible in these depths. This means that the vast majority of deep-sea ecosystems rely on organic matter raining down from the productive surface waters, a phenomenon known as marine snow. This detritus, composed of dead organisms, fecal pellets, and discarded mucus, slowly drifts downwards, providing a sparse but crucial food source for the organisms below. However, in specific locations, a revolutionary alternative energy source exists: chemosynthesis. This process, driven by chemical reactions, forms the base of unique deep-sea communities, particularly around hydrothermal vents and cold seeps. Hydrothermal vents are cracks in the Earth's crust, often associated with volcanic activity along mid-ocean ridges, where superheated, mineral-rich water spews from the seafloor. Chemosynthetic bacteria utilize the chemicals in this vent fluid, such as hydrogen sulfide, as an energy source to produce organic matter, much like plants use sunlight. Cold seeps, in contrast, release methane, hydrogen sulfide, or other hydrocarbon-rich fluids at ambient deep-sea temperatures, also supporting chemosynthetic communities. These chemosynthetic ecosystems are entirely independent of surface sunlight, representing isolated oases of life in the otherwise food-poor deep sea. Another defining characteristic of the deep sea is the immense pressure. For every 10 meters of depth, the pressure increases by approximately 1 atmosphere. At depths of 4,000 meters, the pressure is 400 times greater than at the surface. This crushing force would flatten most surface-dwelling organisms. Deep-sea creatures have evolved specialized cellular and physiological adaptations to withstand this extreme pressure. Their cell membranes are more fluid, containing higher proportions of unsaturated fatty acids, which prevents them from becoming rigid under pressure. Their proteins are structured to maintain their shape and function under high pressure, often by accumulating osmolytes, small organic molecules that stabilize protein structure. Many deep-sea fish, for example, lack swim bladders, which would collapse under the extreme pressure, relying instead on neutral buoyancy, achieved through reduced bone density or high lipid content. Their bodies are often gelatinous or loosely structured, allowing them to withstand pressure changes without suffering internal damage. The perpetual cold of the Antarctic deep sea is a third major environmental constraint. While deep-sea temperatures are generally cold globally, the influence of Antarctic deep water formation makes the Southern Ocean depths particularly frigid. Organisms living here are known as psychrophiles, or cold lovers, meaning their enzymes and metabolic processes are optimized to function at low temperatures. Like the icefish in shallower Antarctic waters, many deep-sea species also possess antifreeze compounds or cold-adapted proteins to prevent ice formation within their cells, even though they are generally not in contact with actual ice crystals. Their metabolic rates are typically very low, a strategy that conserves energy in a food-scarce environment. This results in slow growth rates, extended lifespans, and delayed reproduction compared to their shallow water relatives. Everything in the deep sea moves at a slower pace, a direct consequence of the cold and limited resources. Given the absence of light, many deep-sea creatures have evolved specialized sensory adaptations. While some species possess large, often tubular eyes to maximize the capture of any faint bioluminescence, others have reduced or entirely absent eyes, relying instead on highly developed senses of touch, smell, and pressure detection. The lateral line system in fish, which detects water movements and vibrations, is often highly refined. Chemosensory organs, similar to a sense of smell or taste, are crucial for detecting scarce food particles or chemical cues from potential mates or predators in the vast darkness. Bioluminescence, the production of light by living organisms, is widespread in the deep sea and serves a multitude of purposes. It can be used to attract prey, deter predators, communicate with mates, or even camouflage against faint ambient light from above. The patterns and colours of bioluminescent flashes are incredibly diverse, often species-specific, acting as a form of visual communication in an otherwise dark world. The deep sea near Antarctica is home to a unique assemblage of bizarre creatures, many of which have no counterparts in shallower waters. These include a wide variety of invertebrates and fish. Sponges are particularly abundant in some deep Antarctic areas, forming vast, long-lived communities. These filter feeders draw nutrient-laden water through their bodies, capturing microscopic food particles. Some Antarctic deep-sea sponges are remarkably large, reaching several meters in size, and can live for thousands of years, making them among the oldest living animals on Earth. Their slow growth and longevity are adaptations to the stable, cold environment with limited food. Crinoids, or sea lilies, ancient relatives of starfish, are also found in abundance, often attached to the seafloor by a stalk, filtering food from the water column. Echinoderms, a group that includes starfish, brittle stars, sea cucumbers, and sea urchins, are diverse and common in the Antarctic deep. Giant sea spiders, or pycnogonids, are particularly striking. Some species in the Antarctic deep can reach impressive sizes, with leg spans of up to 75 centimeters, or nearly 30 inches. These creatures move slowly across the sea floor, often preying on small invertebrates or scavenging detritus. Sea cucumbers, or holothurians, are another prevalent group, often seen crawling across the abyssal plains, ingesting sediment and digesting the organic matter within it. Many deep-sea sea cucumbers are remarkably large and can form dense populations. They play an important role in nutrient cycling by processing sediments. Brittle stars are also abundant, using their long, flexible arms to sweep for food particles or scavenge on the seafloor. Some deep-sea starfish are also notably larger than their shallow water relatives, a phenomenon known as deep-sea gigantism. Crustaceans are another diverse group in the Antarctic deep, including various amphipods, isopods, and deep-sea crabs. Giant isopods, resembling oversized pill bugs, can grow to 30 centimeters, or 12 inches, or more in length. These scavengers are well adapted to detecting and consuming carrion that falls from the surface, such as whale carcasses, providing a localized feast in an otherwise food-sparse environment. Various types of deep-sea shrimp and prawns are also found. The abyssal plains are often characterized by fields of manganese nodules and sparse sediment, limiting the attachment points for many organisms, but favoring mobile scavengers and detritivores. The fish in the Antarctic deep sea are also highly adapted. While the white-blooded icefish are more associated with shallower Antarctic waters, various species of deep sea fish, including grenadiers or rat-tails, snailfish, and some types of deep-sea anglerfish, inhabit these depths. Grenadiers are often abundant on the continental slopes and abyssal plains, characterized by large heads and long tapering tails. They are generalist feeders, consuming invertebrates and small fish. Snailfish are another group common in the deep, often having soft, gelatinous bodies and inhabiting the very deepest trenches, with some species found at depths greater than 7,000 meters or 23,000 feet. Deep-sea anglerfish are famous for their bioluminescent lures used to attract prey in the darkness. These fish often have highly reduced bodies relative to their large mouths, allowing them to swallow prey larger than themselves, an adaptation for rare feeding opportunities. The feeding strategies of deep-sea creatures reflect the limited and sporadic food availability. Many are detritivorous, feeding on marine snow and other organic particles that drift down from the surface. Scavengers are crucial for breaking down larger foodfalls, such as whale carcasses or dead fish, which provide massive but infrequent pulses of nutrients. These foodfalls can support vibrant temporary communities of scavengers that rapidly consume the carrion. Predators exist but are generally slow-moving and opportunistic, ambushing prey or relying on lures. Filter feeders, like sponges and crinoids, are common where currents are present to bring food particles to them. Chemosynthetic organisms, as mentioned, form the base of the food web around hydrothermal vents and cold seeps, supporting a unique set of primary consumers, such as giant tube worms, mussels, and clams, which live in symbiosis with chemosynthetic bacteria. These symbiotic relationships allow the invertebrates to derive nutrition directly from the bacteria, bypassing the need to feed on detritus. Antarctica's deep-sea environment is particularly unique due to its connection to the global ocean circulation system. The cold, dense waters formed around Antarctica sink to form Antarctic bottom water, which then flows northward, filling the deepest ocean basins around the world. This means that the Antarctic deep sea is exceptionally cold, even for deep-sea environments. This profound cold stability has implications for the evolution of its deep-sea fauna. Many species here show characteristics similar to those found in the icefish, such as reduced metabolic rates, slow growth, and potentially long lifespans. The deep-sea ecosystems are relatively isolated from those in other oceans, leading to a high degree of endemism, meaning many species are found only in the Southern Ocean deep. Research into these deep-sea environments relies on specialized technology. Remotely operated vehicles, or ROVs, and autonomous underwater vehicles, or AUVs, equipped with cameras, sensors, and manipulators, allow scientists to explore the seafloor, collect samples, and observe organisms in their natural habitat without human presence. Manned submersibles, though less common for routine exploration, provide direct human observation. Bottom trawl nets and dredges are used to collect specimens from the seafloor, though they can be non-selective. Free-falling landers, equipped with cameras and bait, can sit on the seafloor for extended periods, recording the arrival of scavengers and other deep-sea life. These technologies are constantly evolving, enabling scientists to explore ever deeper and gain more detailed insights into these remote ecosystems. Recent discoveries have continually expanded our understanding of Antarctic deep-sea life. In 2022, scientists exploring the Weddell Sea ice shelf revealed a previously unknown ecosystem beneath the ice, comprising diverse sponges, including a potential new species, and other filter-feeding organisms attached to rocks. This discovery, made unexpectedly by a drill hole, demonstrated that life could thrive in conditions of total darkness and extreme cold, far from open water and sunlight, relying on filter feeding from the limited nutrients flowing beneath the ice. This highlights the potential for unexpected deep-sea communities in previously unexplored subglacial and sub-ice shelf environments. Ongoing international research programs, such as those under the auspices of the Scientific Committee on Antarctic Research, continue to map the seafloor, explore new deep-sea habitats, and characterize the biodiversity of these unique ecosystems. The challenges of working in the Antarctic deep sea are immense, including the extreme weather conditions at the surface, the enormous depths, the logistics of deploying and recovering heavy equipment in freezing waters, and the sheer cost of expeditions. Despite these hurdles, the allure of discovery in this alien environment continues to drive scientific exploration, revealing the remarkable resilience and diversity of life in the deepest, coldest corners of our planet. Each expedition brings new surprises, underscoring how much remains unknown about the strange and wonderful creatures that thrive without sunlight in Antarctica's frozen deep. Antarctica, despite its appearance as a sterile, frozen wilderness, teems with an astonishing diversity of microbial life. These tiny organisms, including bacteria, archaea, fungi, and viruses, represent the hidden majority of life on the continent, thriving in conditions that would be lethal to most other forms of existence. From the vast ice sheets and sea ice to subglacial lakes, polar soils, and even within the pores of rocks, microbes have adapted to survive extreme cold, desiccation, high salinity, and prolonged darkness. Their resilience offers profound insights into the limits of life on Earth and has significant implications for the search for extraterrestrial life. Understanding the Antarctic microbe world is crucial for comprehending nutrient cycling, climate processes, and the potential for life in extreme environments beyond our planet. Microbes in Antarctica inhabit a wide array of environments, each presenting unique challenges. The most extensive habitat is the ice itself. This includes the massive continental ice sheets, which can be several kilometers thick, and the annual sea ice that forms and melts around the continent. Within the glacial ice, microbes are trapped during snowfall events and can remain viable, albeit in a dormant state, for hundreds of thousands or even millions of years. Ice cores, drilled from deep within the ice sheet, reveal layers of ancient microbes preserved within the ice matrix. The environment within glacial ice is characterized by extremely low temperatures, high pressure at depth, limited nutrients, and very low water activity. Despite these harsh conditions, specialized psychrophilic, or cold-loving, microbes persist. These microbes are often in a state of stasis, awaiting conditions favorable for resuscitation. Sea ice provides a different microbial habitat. While still very cold, sea ice incorporates brine channels and pockets, small veins of super-concentrated salt water that form as the seawater freezes and excludes salt. These brine channels provide liquid microhabitats where microbes can remain metabolically active even at temperatures below 0 degrees Celsius. Sea ice algae, particularly diatoms, are crucial primary producers within the sea ice, forming the base of a significant food web in the polar oceans. Bacteria and archaea associated with sea ice play vital roles in nutrient cycling, breaking down organic matter and cycling carbon, nitrogen, and phosphorus. The underside of sea ice, bathed in nutrient-rich waters and influenced by light penetration, supports complex microbial communities that are distinct from those within the ice matrix. Perhaps the most fascinating microbial habitats are the subglacial environments, particularly the vast network of subglacial lakes and the underlying bedrock. Subglacial lakes, such as Lake Vostok and Lake Mercer, are bodies of liquid water that lie kilometers beneath the ice sheet, isolated from the Earth's atmosphere for millions of years. These lakes are perpetually dark, under immense hydrostatic pressure from the overlying ice, and at temperatures near the freezing point of water. Despite these extreme conditions, scientific drilling into some of these lakes has confirmed the presence of diverse and active microbial communities. These microbes are entirely independent of sunlight, relying on alternative energy sources for survival. Their isolation for vast geological timescales means they may represent unique evolutionary lineages, entirely different from surface life. The subglacial bedrock itself, and the thin layer of water and sediment at the ice rock interface, also support microbial life. These communities are involved in weathering reactions and nutrient mobilization from the bedrock. Beyond ice and subglacial environments, microbes also inhabit Antarctic soils and rocks. The continent's ice-free areas, such as the dry valleys, represent polar deserts with extremely cold, dry and nutrient-poor soils. Here, microbes dominate the ecosystem, forming visible mats or existing as endolithic communities, meaning they live within the pores and cracks of rocks, protected from harsh surface conditions like ultraviolet radiation and extreme temperature fluctuations. Cyanobacteria, fungi, bacteria, and archaea are found in these soils, often exhibiting adaptations to desiccation and very low temperatures. Similarly, beneath the permafrost, the permanently frozen ground that underlies many of these ice-free areas, dormant and active microbial communities persist, slowly metabolizing nutrients. These terrestrial microbial habitats, while small in area compared to the ice sheets, offer insights into the fundamental adaptations required for life in terrestrial cold deserts. The remarkable ability of Antarctic microbes to survive and even thrive in such harsh conditions stems from a range of specialized adaptations. Many are psychrophiles, meaning they are cold-loving organisms whose enzymes and cellular machinery are optimized to function at low temperatures. Their proteins are more flexible at cold temperatures compared to those from warm-adapted organisms, maintaining their catalytic activity. Their cell membranes often contain a higher proportion of unsaturated fatty acids, which keeps them fluid and functional at sub-zero temperatures, preventing them from becoming rigid and dysfunctional. To prevent intracellular ice formation, which is lethal to most cells, many Antarctic microbes produce cryoprotectants, or antifreeze compounds, such as sugars, amino acids, and polyols, that accumulate within their cells. These compounds act like antifreeze, lowering the freezing point of the cytoplasm and preventing ice crystal growth. Another critical survival strategy for Antarctic microbes is dormancy. When environmental conditions become too extreme, such as during periods of extreme cold, desiccation, or nutrient scarcity, many microbes can enter a state of suspended animation, greatly reducing their metabolic activity and preserving cellular components. They can remain in this dormant state for extended periods, even millions of years within ancient ice. When more favorable conditions return, such as the presence of liquid water or nutrients, these microbes can resuscitate and become metabolically active again. This ability to enter and exit dormancy is key to their long-term survival in variable and harsh polar environments. Some microbes have also developed highly efficient DNA repair mechanisms to counteract damage caused by radiation or other stresses during prolonged dormancy. Energy acquisition in the deep, dark, and often nutrient-poor environments is another fundamental challenge. While surface microbes might rely on photosynthesis, those in the deep ice, subglacial lakes, or rocks must find alternative energy sources. Chemosynthesis is a primary strategy, similar to what is seen in deep-sea animals. These microbes utilize chemical reactions involving inorganic compounds to produce organic matter. For instance, some microbes are lithoautotrophs, meaning they eat rock, deriving energy from the oxidation of inorganic compounds found in minerals and rocks, such as iron, sulfur, or hydrogen. Others may use methane or hydrogen sulfide as energy sources. In the absence of light, these chemolithoautotrophs form the base of localized food webs, supporting other microbial life forms that consume the organic matter produced. Organic matter that is buried or seeps into these deep environments, originating from ancient sediments or transported by meltwater, also provides a limited but crucial energy source for heterotrophic microbes, which consume pre-existing organic compounds. The ecological roles of microbes in Antarctica are profound and far-reaching, despite their microscopic size. They are the primary drivers of biogeochemical cycles in many of these extreme environments, mediating the cycling of essential elements such as carbon, nitrogen, sulfur, and phosphorus. In marine environments, sea ice algae and bacteria form the base of the food web, supporting krill and ultimately whales, seals, and penguins. In terrestrial environments, soil microbes are responsible for nutrient turnover and decomposition. In subglacial lakes, they represent a unique primary producer community, sustaining potentially isolated ecosystems. They are also crucial in the weathering of rocks, slowly breaking down minerals and releasing nutrients. Their ability to adapt to such harsh conditions makes them crucial indicators of ecological resilience and the fundamental processes that sustain life in extreme environments. The study of Antarctic microbes has significant implications for astrobiology, the search for life beyond Earth. Many extraterrestrial environments in our solar system, such as the subsurface oceans of icy moons like Europa and Enceladus, or the polar ice caps of Mars, share characteristics with Antarctic extreme habitats. These moons are thought to harbour vast liquid water oceans beneath thick ice shells, similar in concept to Antarctic subglacial lakes. The discovery of active microbial life in Antarctica's subglacial lakes, thriving in perpetual darkness and under immense pressure without sunlight, provides a powerful analogue for how life might exist on these extraterrestrial bodies. If life can persist in such conditions on Earth, it increases the likelihood that similar life forms could exist in analogous environments elsewhere. Understanding the metabolic strategies, survival mechanisms, and biodiversity of Antarctic extremophiles helps astrobiologists formulate hypotheses about where to look for extraterrestrial life and what types of biosignatures to search for. For instance, the reliance on chemosynthesis or lithoautotrophy by Antarctic deep microbes offers a model for potential energy sources for alien life in environments devoid of sunlight. Research methods for studying Antarctic microbes are highly specialized due to the extreme conditions and the need to prevent contamination. Ice core drilling is a primary technique, allowing scientists to retrieve pristine samples of ancient ice from kilometers deep within the ice sheet. These cores are carefully handled to prevent contamination from drilling fluids or surface microbes. Once retrieved, the ice is melted in sterile conditions, and the trapped microbes are cultured or analysed using molecular techniques such as DNA sequencing. This allows scientists to identify the types of microbes present and to study their genetic makeup, revealing their evolutionary history and adaptive genes. For subglacial lakes, the challenge is even greater, requiring ultra-clean drilling techniques that minimise the risk of introducing foreign microbes from the surface. Specialised hot water drills or mechanical drills with sterilised reamers are used to create boreholes, and sampling instruments are meticulously sterilised. The aim is to retrieve samples that truly represent the isolated subglacial environment. Beyond culturing and DNA sequencing, metagenomics, the study of genetic material recovered directly from environmental samples without the need for culturing, has revolutionised the study of Antarctic microbes. This approach allows scientists to identify the full range of microbial diversity present in a sample, including those that are difficult or impossible to grow in a laboratory. Metagenomics also provides insights into the metabolic potential of microbial communities by identifying the genes encoding specific enzymes or metabolic pathways. This helps to understand how these communities function and interact in their extreme environments. Stable isotope analysis is another powerful tool, which involves measuring the ratios of different isotopes of elements like carbon, nitrogen, or sulfur in microbial cells. These isotopic signatures can reveal the metabolic pathways microbes use and their sources of energy, providing direct evidence for processes like chemosynthesis in deep, dark environments. Recent discoveries have continually expanded our knowledge of the Antarctic microbe world. In 2013, a team successfully drilled into and sampled Lake Whillans, a subglacial lake in West Antarctica, confirming the presence of a diverse and active microbial ecosystem. The microbes were found to be metabolically active, using chemical energy derived from minerals and the breakdown of ancient organic matter. This was a major breakthrough, proving that life could thrive in these deeply isolated environments. Similar discoveries have since been made in other subglacial lakes, including Lake Mercer in 2018, where scientists found evidence of both active microbial life and ancient animal remains, raising further questions about the interaction between the subglacial ecosystem and larger forms of life. The discovery of novel viruses within ancient Antarctic ice cores has also opened up new avenues of research into the viral ecology of extreme environments and their potential role in microbial evolution. The study of microbes living within the bedrock itself, at the interface with the ice, continues to reveal extremophiles adapted to life within rock fractures and beneath immense geological pressure. The challenges of studying Antarctic microbes are formidable. The extreme cold, remoteness, and logistical difficulties make fieldwork incredibly complex and expensive. Preventing contamination of samples, especially for ancient ice and subglacial lake environments, is paramount and requires stringent sterile protocols. Many Antarctic microbes are slow-growing or unculturable in laboratory settings, posing difficulties for traditional microbiological techniques. Despite these hurdles, the ongoing exploration of Antarctica's microbe world is continually revealing new forms of life and astonishing adaptations. These tiny organisms, often unseen and unappreciated, hold keys to understanding the fundamental limits of life, the planet's past climate, and the exciting possibilities for life beyond Earth. They represent a vibrant, resilient, and largely unexplored biosphere hidden beneath the frozen veil of the Antarctic continent. Antarctica, as it exists today, is largely defined by its immense ice sheets, which cover approximately 98% of its landmass. However, this frozen continent was not always a realm of ice. Over vast geological timescales, Earth's climate has undergone profound changes, and Antarctica's position on the planet's surface has shifted dramatically due to plate tectonics. These transformations mean that beneath the kilometers of ice that now blanket the continent lie the remnants of ancient ecosystems, landscapes, and life forms that thrived when Antarctica was a vastly different place. The idea of these lost ecosystems, trapped and preserved in a frozen state, offers a rare glimpse into Earth's deep past, revealing chapters of biodiversity and environmental conditions that existed millions of years ago. These buried worlds provide crucial evidence for understanding planetary climate shifts, continental drift, and the remarkable resilience of life. To understand these lost ecosystems, it is necessary to journey back in geological time to when Antarctica was part of the supercontinent Gondwana. Around 180 million years ago, Gondwana began to break apart, but for a significant period before and during its initial fragmentation, Antarctica was located in much warmer, more temperate latitudes. It was connected to South America, Africa, India, and Australia. During the Mesozoic era, particularly in the Cretaceous period, between 145 and 66 million years ago, Antarctica was free of ice. Paleontological and geological evidence from exposed rock formations on the continent and from sedimentary cores drilled offshore confirm a radically different climate. This ancient Antarctica was covered in lush vegetation, including vast forests, and supported a diverse array of terrestrial and marine animal life. The climate was warm enough to sustain extensive flora and fauna, far removed from the desolate cold of today. One of the most compelling pieces of evidence for ancient Antarctic ecosystems comes from plant fossils. Fossils of temperate and even subtropical vegetation have been discovered in various ice-free regions of Antarctica, particularly on the Antarctic Peninsula and in the Transantarctic Mountains. A prime example is the discovery of Glossopteris fossils. Glossopteris was a tree-like plant with tongue-shaped leaves that dominated the ancient supercontinent Gondwana during the Permian period, roughly between 299 and 252 million years ago. The presence of Glossopteris fossils in Antarctica, identical to those found in South America, Africa, India, and Australia, was one of the key pieces of evidence that supported Alfred Wegener's theory of continental drift in the early 20th century. These fossils indicate a period when Antarctica was part of a larger landmass and experienced a climate warm enough to support widespread forests. Later, during the Cretaceous period, fossils of Nothofagus, or southern beech, a tree common in temperate southern hemisphere regions today, have been found. These findings suggest that for millions of years, Antarctica hosted diverse forested ecosystems, ranging from temperate rainforests to more open woodlands, depending on the specific geological epoch and regional climate. Beyond plant life, the fossil record also reveals the presence of animal life in ancient Antarctica. Perhaps most strikingly, dinosaur fossils have been discovered on the continent. In 1986, scientists discovered the remains of Antarctopelta oliveroi, an armoured dinosaur, on James Ross Island off the Antarctic Peninsula. This was the first definitive dinosaur found on the continent. Subsequent discoveries include Cryolophosaurus elioti, a large carnivorous theropod found in the Transantarctic Mountains in 1991. This dinosaur lived during the early Jurassic period, about 190 million years ago, indicating that large active predators roamed Antarctica when it was warmer and part of Gondwana. Other dinosaur finds include ornithopods and sauropods. These discoveries paint a picture of a continent where dinosaurs grazed on ancient vegetation and preyed upon other animals, much like their counterparts on other continents. The presence of such large terrestrial animals further underscores the mild climate that prevailed, as dinosaurs, being ectothermic, would not have survived the extreme cold of modern Antarctica. The transition from a forested, dinosaur-populated continent to an ice-covered realm began gradually. As Gondwana continued to break apart, Antarctica eventually separated from South America and Australia approximately 45 to 34 million years ago. This separation opened up gateways for ocean currents to flow unimpeded around the continent, leading to the formation of the Antarctic Circumpolar Current. This powerful current acted as a thermal barrier, isolating Antarctica from warmer ocean waters and initiating a dramatic cooling trend. As temperatures dropped, snowfall accumulated year after year, and glaciers began to form and expand. Over millions of years, these individual glaciers coalesced into vast ice sheets, slowly but relentlessly advancing across the continent. This process of glaciation effectively buried the existing landscapes, including forests, river valleys, and mountains, preserving them beneath an ever-thickening layer of ice. The sheer weight of the ice pressed down on the underlying land, compacting and sealing away the remnants of these ancient ecosystems. The mechanisms by which these ancient ecosystems are preserved under the ice are a combination of factors unique to the polar environment. The primary mechanism is the deep freeze. The extreme cold, with temperatures consistently below freezing, effectively halts the processes of decomposition and decay that would normally break down organic matter in warmer environments. Microbes responsible for decomposition are either rendered inactive or significantly slowed by the low temperatures. This allows organic materials from fossilized wood and leaves to the remains of ancient animals to be preserved for millions of years. Furthermore, in many areas beneath the thick ice, there is a distinct lack of oxygen. These anaerobic conditions further inhibit the activity of aerobic decomposers, contributing to the preservation of organic material. The immense pressure from the overlying ice also compacts and protects the buried features from physical weathering and erosion by wind or liquid water. The ice acts as a protective shield, sealing the ancient landscapes and their biological remnants from the destructive forces of the surface environment. While direct fossil evidence is found in ice-free regions, the ice sheet itself holds indirect, and sometimes direct, evidence of past ecosystems. Ice cores, drilled from kilometers deep into the ice sheet, act as time capsules. As snow falls and compacts into ice, it traps tiny particles from the atmosphere, including pollen grains, fungal spores, and microscopic fragments of ancient vegetation. By analysing these trapped biological particles in ice cores, scientists can reconstruct the types of plants and vegetation zones that existed on Antarctica and the surrounding continents during different geological periods. For example, pollen from ancient conifer trees and flowering plants can be identified, providing evidence for warmer intervals when plant life was more widespread. Furthermore, ancient DNA, though often degraded, has been successfully extracted from ice cores, revealing the genetic signatures of microbial communities and even remnants of larger organisms that existed thousands to hundreds of thousands of years ago. These genetic traces provide another line of evidence for past biodiversity. The topography of the land hidden beneath the ice also provides clues about these lost ecosystems. Ice-penetrating radar surveys have revealed a landscape of buried mountains, vast river valleys, and ancient lake basins, all sculpted by geological and hydrological processes that occurred before glaciation. These subglacial features are not merely geological curiosities, they represent the physical remnants of the landscapes upon which these lost ecosystems thrived. For example, the discovery of ancient river systems beneath the East Antarctic ice sheet indicates that liquid water once flowed freely across the continent, supporting a terrestrial hydrological cycle conducive to life. The shape of these buried valleys and plains directly reflects the terrain that existed when forests and dinosaurs roamed Antarctica. The immense Gamburtsev Mountains, hidden beneath thousands of meters of ice in East Antarctica, are thought to have played a role in the initial growth of the ice sheet, but before their burial, they would have been prominent geographical features of a temperate continent. The scale of these lost ecosystems is vast. During the peak of its warmer periods, Antarctica was likely covered by extensive forests, perhaps stretching from its interior to its coasts. These would have been complex ecosystems with a diverse array of plants, insects, and vertebrates. The types of forests varied over time, from ancient coniferous forests and ferns during the Mesozoic to Nothofagus-dominated forests in the early Cenozoic. The presence of dinosaurs suggests a food web supporting large herbivores and carnivores. Marine ecosystems around the continent would also have been vastly different, supporting a wider array of warm water-adapted marine life before the onset of extreme cold. The current fossil record, though sparse due to the difficulty of accessing and sampling the continent's geology, offers tantalizing hints of what lies beneath the ice. Beyond the macroscopic world of plants and animals, the concept of lost ecosystems also extends to microbial life trapped within the ice. As snow falls and accumulates, it can trap microorganisms from the atmosphere or from the terrestrial surface. These microbes, once encased in the ice, can remain dormant but viable for millions of years. Deep ice cores contain ancient bacteria, archaea, and viruses that represent microbial communities from past epochs. While these are not ecosystems in the traditional sense of complex interactions among diverse species, they represent preserved remnants of past microbial biodiversity. Their potential for resuscitation provides a direct link to ancient life forms and their unique biochemical pathways. The sediments beneath subglacial lakes, isolated for millions of years, are also thought to contain ancient microbial communities, and possibly even macrofossil remains, that existed on the land before the ice sheet formed. The exploration of these lost ecosystems faces immense challenges. The primary obstacle is the sheer thickness of the ice, which makes direct access to the underlying bedrock and ancient sediments extremely difficult and costly. Drilling through kilometers of ice requires specialized equipment and expertise. Even when bedrock samples are obtained, they are often small and come from very remote, isolated locations. Furthermore, the risk of contaminating pristine ancient samples with modern microbes during drilling operations is a constant concern, requiring stringent sterile protocols. Despite these difficulties, ongoing scientific endeavors, utilizing ice-penetrating radar, geological surveys in ice-free areas, and deep ice core drilling continue to piece together the story of Antarctica's ancient past. The significance of studying these lost ecosystems is multifaceted. Firstly, they provide crucial data for understanding past global climates. The transition of Antarctica from a forested continent to an ice-covered one serves as a powerful natural experiment in climate change, offering insights into the long-term impacts of atmospheric and oceanic shifts. Secondly, they offer a unique perspective on the evolution of life. The discovery of ancient species and lineages, particularly microbes, can shed light on how life adapts and diversifies over geological timescales. Thirdly, they contribute to our understanding of plate tectonics and paleogeography, refining models of how continents have moved and reconfigured throughout Earth's history. Finally, these buried ecosystems raise profound questions about preservation and the potential for ancient life to survive under extreme conditions, which has implications for the search for life on other planets, particularly those with ice-covered surfaces like Mars or icy moons in our outer solar system. The secrets held beneath Antarctica's ice continue to inspire scientific exploration, revealing the remarkable and dynamic history of our planet's living surface. Beneath the immense ice sheets of Antarctica, hidden from direct view and isolated from the Earth's atmosphere for millions of years, lies a vast network of liquid water bodies known as subglacial lakes. These are not merely isolated pockets of water, but can be vast, deep lakes, sometimes interconnected by subglacial rivers and channels, forming an extraordinary hydrological system beneath the ice. The existence of these liquid lakes beneath kilometers of solid ice was once a theoretical concept, but scientific advancements, particularly in ice-penetrating radar technology, have conclusively confirmed their presence. The discovery of these lakes has revolutionized our understanding of Antarctica's true geography, its dynamic ice sheet, and the potential for life in extreme, previously unimaginable environments. They represent one of the Earth's most significant unexplored frontiers. The first major subglacial lake to be unequivocally confirmed was Lake Vostok, located beneath nearly 4 kilometers or 2.5 miles of ice in East Antarctica. Initial hints of its existence came from seismic surveys conducted by Soviet researchers in the 1970s, which detected an unusual flat, strong reflection at the base of the ice. Subsequent ice-penetrating radar surveys by British scientists in the 1990s provided compelling evidence of a large body of liquid water. Lake Vostok is enormous, stretching approximately 250 kilometers or 155 miles in length and 50 kilometers or 31 miles in width. with depths that can exceed 1,000 meters or 3,300 feet. Its size is comparable to North America's Lake Ontario. Following the confirmation of Lake Vostok, extensive radar surveys across the entire continent have since identified over 400 distinct subglacial lakes, with more likely awaiting discovery. These lakes vary greatly in size, from small ponds to vast bodies of water, and are found beneath both the east and west Antarctic ice sheets, often concentrated in areas of topographic depressions, or where ice flow is particularly slow. The question of how these lakes remain liquid despite being buried under such immense volumes of ice in a continent renowned for its extreme cold is central to their mystery. Several key factors combine to create and maintain these subglacial aquatic environments. The most significant factor is geothermal heat flux. Earth's interior generates heat that continuously flows outwards to the surface. While the amount of heat is relatively small in most places, it is sufficient to melt ice at the base of the ice sheet if that heat is effectively trapped. The thick ice sheet itself acts as a massive insulating blanket, trapping the geothermal heat from below and preventing it from dissipating rapidly into the extremely cold atmosphere above. This trapped heat warms the bedrock at the base of the ice, causing the overlying ice to melt. In areas with higher than average geothermal heat flux, such as those near active subglacial volcanoes or tectonic rift systems, the rate of basal melting is even greater, contributing more significantly to lake formation. A second crucial factor is pressure melting. Ice, unlike most solids, exhibits a property where its melting point decreases under increasing pressure. For every 100 meters of overlying ice, the melting point of water decreases by approximately 0.01 degrees Celsius. Given that subglacial lakes can be buried under several kilometers of ice, the pressure at their base is enormous, hundreds of times greater than atmospheric pressure. This immense pressure effectively lowers the melting point of the ice at the base to slightly below 0 degrees Celsius, allowing it to remain liquid even at temperatures that would typically cause water to freeze at the surface. For example, at a depth of 4,000 meters of ice, the melting point of water is lowered to around -2 degrees Celsius. So, if the temperature at the ice bedrock interface is, say, -1.5 degrees Celsius, the ice will melt due to the pressure. A third contributing factor is frictional heat. As the massive ice sheet slowly flows over the underlying bedrock, friction is generated at the ice bed interface. This friction, though small at any single point, accumulates over the vast areas of contact, generating a considerable amount of heat. This frictional heat contributes to basal melting, especially in areas of faster ice flow, such as ice streams, where it can provide a significant source of energy for meltwater production. The combination of geothermal heat, pressure melting, and frictional heat ensures that a thin layer of water, or even large lakes, can persist at the base of the ice sheet, providing lubrication for ice flow and creating unique habitats for life. The characteristics of subglacial lakes are profoundly different from surface lakes. They are perpetually dark, as no sunlight can penetrate through kilometers of ice. This means that any life within them must be completely independent of photosynthesis, relying on alternative energy sources. They are also under immense hydrostatic pressure, which influences the physiology of any organisms living there. The water composition can vary significantly between lakes, influenced by the geochemistry of the underlying bedrock, the interaction with ancient sediments, and the input of meltwater. Some lakes may be rich in dissolved gases, such as oxygen or methane, trapped from ancient ice or produced by microbial activity. Lake Vostok, for example, is thought to be highly oxygenated due to the slow infusion of gases from the ice above. Other lakes might be anoxic, lacking oxygen, creating conditions suitable for anaerobic microbes. The water in these lakes can also be quite old, having been isolated for millions of years, which may lead to unique chemical compositions and nutrient limitations. The isolation of subglacial lakes from the Earth's surface for vast geological timescales is one of their most intriguing aspects. Lake Vostok is estimated to have been isolated for at least 15 million years, and possibly even longer. This extreme isolation implies that any life forms within these lakes have evolved independently for extended periods, adapting to their unique conditions without influence from surface ecosystems. Such isolation could lead to the discovery of novel species, unique genetic lineages, and even entirely new branches on the tree of life, distinct from anything known on the surface. These lakes are pristine environments, protected from modern human contamination, making them invaluable for scientific study. The primary focus of research on subglacial lakes has been the search for life. The presence of liquid water, even in extreme conditions, suggests the possibility of microbial ecosystems. However, accessing these lakes to sample them without contaminating their pristine environments is a monumental challenge. The international scientific community has developed stringent ultra-clean drilling protocols to minimize this risk. These methods involve using hot water drills that melt a borehole through the ice, with the meltwater continuously filtered and sterilized, or specialized mechanical drills with multiple casing systems and meticulous sterilization of all equipment. The goal is to obtain uncontaminated samples of lake water and sediment that truly represent the isolated subglacial environment. One of the most significant breakthroughs in subglacial lake exploration came in 2013, when a team of American scientists successfully drilled into and sampled Lake Whillans, a smaller subglacial lake in West Antarctica. Unlike Lake Vostok, which is thought to be more isolated, Lake Whillans is part of a larger dynamic subglacial hydrological system. The Lake Whillans drilling team successfully collected water and sediment samples and found compelling evidence of a diverse and active microbial ecosystem. The microbes identified were bacteria and archaea, living by chemosynthesis, meaning they derive energy from chemical reactions rather than sunlight. They were found to be metabolically active, utilizing chemical energy from the oxidation of various inorganic compounds found in the underlying bedrock, such as sulfur and iron, and from the breakdown of ancient organic carbon that had been trapped in the sediments. This discovery provided the first direct evidence that active microbial life can thrive in these deeply isolated, perpetually dark environments. Following the success at Lake Whillans, another significant discovery occurred in 2018 when scientists drilled into Lake Mercer, also in West Antarctica. Samples from Lake Mercer also revealed a diverse microbial community, again relying on chemosynthesis. Intriguingly, initial analyses of Lake Mercer sediments also suggested the presence of ancient animal remains, including the DNA of small crustaceans and a possible tardigrade, or water bear. While these were likely remnants from a time when the lake was open to the surface, before glaciation, it raises fascinating questions about the preservation of macro life and the potential for a more complex ancient ecosystem that was eventually buried and preserved. These discoveries continue to push the boundaries of what we consider habitable environments on Earth. The types of life found in subglacial lakes are primarily microbial. These are extremophiles, organisms adapted to extreme conditions. They are psychrophils, thriving in the cold. Many are also barophils, or piezophiles, meaning they are pressure-loving, adapted to the immense pressures at depth. Their metabolic strategies are diverse, primarily relying on chemosynthesis, either lithoautotrophy, where they get energy from inorganic rock materials, or by breaking down ancient organic matter. They represent unique adaptations, potentially having evolved different biochemical pathways and enzymes to cope with their extreme isolation and environment. The potential for discovering novel microbial species with unique metabolic capabilities is high. While currently there is no evidence of complex multicellular life living actively within the lakes themselves, the discovery of ancient animal DNA in Lake Mercer sediments highlights the possibility of finding such remains, or perhaps dormant forms if the conditions for preservation are right. Beyond their biological significance, subglacial lakes also play a crucial role in ice sheet dynamics. The presence of liquid water at the base of the ice sheet acts as a lubricant, reducing friction between the ice and the bedrock. This basal lubrication can significantly increase the speed of ice flow, contributing to the movement of vast ice streams towards the coast. Changes in the subglacial hydrological system, such as the draining and filling of lakes, can have a direct impact on the stability and speed of overlying ice streams. Scientists have observed instances where subglacial lakes rapidly drain into other lakes or the ocean, causing the overlying ice to accelerate temporarily. Understanding the distribution and dynamics of these subglacial lakes and their interconnectedness is therefore crucial for accurate models of ice sheet behavior and for predicting future contributions to global sea level rise. The sediments beneath subglacial lakes also hold immense potential for paleoclimate research. These sediments accumulate slowly over millions of years and contain layers of rock fragments, minerals, and organic matter that settled from the water column. Unlike surface sediments, they are protected from disturbance by glacial erosion or wind, offering continuous and undisturbed records of past environmental conditions. Analysing these sediments can reveal information about the geological history of the continent, past volcanic eruptions, and even long-term climate variability, offering insights into periods extending far beyond the reach of ice core records. The chemical composition of the lake water itself can also provide clues about long-term geological processes and water-rock interactions. The study of subglacial lakes has profound implications for astrobiology. These lakes serve as natural analogues for potential subsurface oceans on icy moons in our outer solar system, such as Europa, a moon of Jupiter, and Enceladus, a moon of Saturn. Both moons are thought to harbour vast liquid water oceans beneath thick ice shells, sustained by tidal heating and potentially interacting with a rocky core. If life can thrive in Antarctica's subglacial lakes, isolated from sunlight and relying on chemosynthesis, it significantly increases the likelihood that similar life forms could exist in the subsurface oceans of these extraterrestrial worlds. The methods developed for exploring Antarctic subglacial lakes, particularly the ultra-clean drilling technologies, are directly applicable to future missions designed to sample extraterrestrial oceans. The types of metabolic pathways discovered in Antarctic subglacial microbes also inform astrobiologists about the potential biochemistry of alien life. The challenges in studying subglacial lakes remain substantial. The extreme remoteness, the logistical complexity, and the harsh environmental conditions make fieldwork incredibly difficult and expensive. The primary scientific and ethical imperative is to avoid contaminating these pristine environments, meaning every piece of equipment that enters the borehole must be meticulously cleaned and sterilized. The technological hurdles are immense, requiring specialized drills and sensors that can operate effectively under extreme pressure and cold. Despite these challenges, the allure of discovering new forms of life and unlocking secrets about Earth's deep past and the potential for life beyond our planet continues to drive international scientific collaboration and innovation in exploring Antarctica's hidden subglacial lakes. Each successful mission brings humanity closer to understanding these extraordinary isolated worlds beneath the ice. The continent of Antarctica, presently a vast expanse of ice and snow, holds within its geological record a profound secret. It was once a land of lush, thriving forests. This startling contrast to its current frozen state reveals a dramatic story of planetary climate change and continental transformation that spans hundreds of millions of years. The evidence for these ancient forests comes from the fossilized remains of plants, found in exposed rock formations on the continent's fringes and from microscopic pollen grains, extracted from deep sediment and ice cores. These discoveries paint a picture of a vastly different Antarctica, a land teeming with vegetation, supporting a complex web of life that bears no resemblance to the stark polar desert of today. Understanding how this verdant past transitioned to the icy present is crucial for comprehending Earth's long-term climate dynamics. The story of Antarctica's ancient forests begins not with climate, but with plate tectonics. For much of its history, Antarctica was not positioned at the South Pole. Instead, it was a central component of the supercontinent Gondwana, which existed from roughly 600 million years ago until about 180 million years ago, when it began to break apart. During the Permian period, approximately 299 to 252 million years ago, Antarctica was situated at higher latitudes, but still experienced a more temperate climate due to different global atmospheric conditions and continental configurations. As Gondwana gradually fragmented over the Mesozoic era, Antarctica began its slow, inexorable drift southward. However, for tens of millions of years, even as it drifted, its connections to other land masses, such as Australia and South America, and global atmospheric and oceanic circulation patterns, kept its climate relatively mild, far too warm for the widespread glaciation seen today. One of the most iconic pieces of evidence for ancient Antarctic forests is the fossil plant Glossopteris. This distinctive fern-like tree, with its tongue-shaped leaves, was a dominant flora across Gondwana during the Permian period. Fossils of Glossopteris are found not only in Antarctica but also in South America, Africa, India and Australia. The presence of identical Glossopteris fossils across these now widely separated continents was one of the cornerstone pieces of evidence that supported the theory of continental drift, proposed by Alfred Wegener in the early 20th century. These fossils indicate that during the Permian, Antarctica was not ice-covered, but supported extensive forests or swampy woodlands where Glossopteris thrived. The climate during this period must have been warm enough to sustain such a widespread and productive ecosystem, with sufficient rainfall and temperatures that did not experience prolonged freezing conditions. Moving into the Mesozoic era, the age of dinosaurs, roughly between 252 and 66 million years ago, Antarctica continued to host forests. During the Jurassic and Cretaceous periods, the continent was still largely ice-free and characterized by forested landscapes. Fossil evidence from this period includes a variety of conifers, cycads, and ferns. Conifers, such as those related to modern pines and spruces, would have formed the canopy, while ferns and other low-growing plants created a lush understory. The discovery of fossilized wood, complete with tree rings, provides further insights. The presence of distinct tree rings indicates seasonal growth patterns, suggesting that while the climate was warm, there were still periods of slower growth, likely influenced by the polar light cycle, with extended periods of daylight in summer and prolonged darkness in winter, even in a milder climate. These forests would have provided habitats and food sources for the dinosaurs and other prehistoric animals that roamed the continent. The early Cenozoic era, immediately following the extinction of the dinosaurs around 66 million years ago, continued to be a period of forested Antarctica, albeit with a gradual cooling trend. During the Paleocene and Eocene epochs, roughly 66 to 34 million years ago, Antarctica experienced warm, wet conditions, particularly in its coastal regions. Fossil evidence from this period includes Nothofagus, or southern beech, a genus of trees still found in temperate regions of the southern hemisphere today, such as South America, Australia and New Zealand. The discovery of Nothofagus fossils in Antarctica strongly suggests the presence of extensive temperate rainforests or moist woodlands. These forests would have been dominated by Nothofagus species, along with a diverse array of other flowering plants and ferns. The presence of such flora indicates that temperatures remained mild, likely above 10 degrees Celsius or 50 degrees Fahrenheit for much of the year, with ample precipitation, creating a truly verdant landscape across parts of the continent. The evidence from these ancient plant fossils allows scientists to reconstruct the climate of ancient Antarctica. The types of plants found, particularly those requiring mild, frost-free conditions and ample moisture, indicate average annual temperatures significantly warmer than today. For example, the presence of evergreen temperate rainforest species implies that winter temperatures rarely dropped below freezing for extended periods. Precipitation levels must have been high enough to support dense forest growth, suggesting a much wetter environment. While the overall temperatures were warm, the high latitude position of Antarctica meant that these forests still experienced extreme seasonal light cycles, with periods of 24-hour daylight in summer and prolonged darkness in winter. The plants would have evolved adaptations to cope with these unique light regimes, perhaps through periods of dormancy or slower metabolic activity during the long polar night, even without freezing temperatures. This contrasts sharply with current Antarctic conditions, where temperatures rarely rise above freezing and precipitation largely falls as snow. Microscopic fossil evidence further corroborates the picture of ancient forests. Pollen grains and spores, preserved in marine sediment cores drilled off the coast of Antarctica, and occasionally within ancient ice core layers, provide detailed records of past vegetation. These microfossils, being incredibly resistant to decay, can be transported by wind and water over vast distances and settle in sediments. Analysis of pollen assemblages allows paleontologists to identify the types of plants that were dominant in different time periods, even in areas where macrofossils are scarce. For example, high concentrations of Nothofagus pollen in sediment cores dating back to the Eocene provide strong evidence for widespread beech forests across the continent before glaciation. Changes in pollen types and abundance through geological strata directly reflect the shifting vegetation patterns as Antarctica cooled and its forests gradually disappeared. The drastic climate change that transformed Antarctica from a lush, forested land to its current icy state was a monumental event driven by a combination of continental drift and changes in global atmospheric and oceanic circulation. The critical turning point occurred roughly 34 million years ago at the Eocene-Oligocene boundary. By this time, Antarctica had drifted to a position very close to the South Pole. More importantly, it had finally separated definitively from Australia and South America. The opening of the Drake Passage between South America and the Antarctic Peninsula, and the Tasman Gateway between Antarctica and Australia, allowed for the unimpeded flow of ocean currents around the continent. This led to the formation of the Antarctic Circumpolar Current, a powerful, cold current that effectively isolated Antarctica from warmer ocean waters. Once the Antarctic Circumpolar Current was established, it created a thermal barrier preventing warmer waters from reaching the continent's shores. This isolation initiated a rapid and dramatic cooling trend. As temperatures plummeted, snow began to accumulate year after year, and seasonal snow cover eventually gave way to perennial snow and then small glaciers. These glaciers expanded, coalescing into larger ice caps, and ultimately growing into the vast continental ice sheets we see today. This process was accelerated by positive feedback loops, particularly the ice albedo effect. As more snow and ice covered the continent, more sunlight was reflected back into space, leading to further cooling and thus more ice accumulation. This self-perpetuating cycle rapidly transformed the continent's climate and landscape. Evidence for this cooling and glaciation comes from marine sediment cores around Antarctica, which show a sharp increase in ice-rafted debris, indicating the presence of major glaciers and ice sheets breaking off into the ocean. Chemical analyses of fossil shells and sediments also show a clear shift towards colder ocean temperatures. The transformation was not instantaneous but occurred over millions of years. The warm, adapted forests gradually retreated, replaced by more cold, tolerant vegetation, and eventually by no terrestrial vegetation at all in the interior as the ice sheets expanded. Some species would have gone extinct, while others might have migrated to other landmasses if corridors still existed. The transition from a greenhouse world with high atmospheric carbon dioxide levels to an icehouse world with lower carbon dioxide levels also played a significant role in this climatic shift, influencing global temperatures and precipitation patterns that facilitated glaciation. The remnants of these ancient forests now lie buried beneath kilometers of ice, a testament to the planet's dynamic history and the profound impact of long-term climate change. Studying these lost ecosystems of Antarctica holds immense modern relevance. Firstly, they provide a natural laboratory for understanding Earth's climate sensitivity to changes in atmospheric carbon dioxide and continental configurations. The past transition from a warm, forested Antarctica to an icy one demonstrates the dramatic effects of greenhouse gas concentrations and ocean circulation patterns. This historical context helps scientists refine models of future climate change and predict the potential impacts of continued global warming on polar ice sheets and sea levels. Secondly, these ancient ecosystems offer insights into the resilience and vulnerability of life in response to environmental shifts. The adaptive strategies of plants and animals that thrived in a polar but warm environment, and their eventual disappearance, provide valuable lessons for modern biodiversity conservation in a changing world. The challenges of discovering and studying these ancient forests are considerable. The vast majority of the continent's landmass is covered by kilometers of ice, making access to the underlying rock formations extremely difficult. Only a small fraction of the continent, primarily coastal regions and nunataks, which are mountain peaks that protrude through the ice, expose geological strata. Fieldwork in these exposed areas is arduous, conducted in extreme cold, high winds and remote conditions, requiring extensive logistical support. Dating fossil finds accurately can also be challenging. Despite these difficulties, ongoing scientific expeditions continue to uncover new fossil sites and refine our understanding of Antarctica's green past. The existence of these lost ecosystems beneath the ice is a powerful reminder of Earth's ever-changing face and the profound capacity of both geological and biological processes to transform continents over geological timescales. The frozen deep holds the keys to a forgotten, vibrant past, constantly challenging our perceptions of this icy land. Antarctica, currently a continent of extreme cold and vast ice sheets, was once a land where dinosaurs roamed freely, thriving in an environment far removed from the icy desolation of today. The fossil evidence for these prehistoric creatures paints a vivid picture of a distant past, revealing a period when Antarctica was part of the supercontinent Gondwana and experienced a climate warm enough to support diverse dinosaurian and other ancient life forms. This chapter will delve into the remarkable discoveries that confirm Antarctica as a dinosaur land, exploring the types of dinosaurs and other prehistoric animals that inhabited it, the environment they lived in, and the profound implications these findings have for understanding global paleogeography and the history of life on Earth. For much of the Mesozoic era, the age of dinosaurs, roughly between 252 and 66 million years ago, Antarctica was not located at the South Pole. Instead, it was situated at more southerly but still temperate latitudes as a central component of the supercontinent Gondwana. This continental configuration, combined with higher global atmospheric carbon dioxide levels, meant that the climate of Antarctica was significantly warmer than it is today. There were no continental ice sheets, and much of the land was covered by forests, rivers and wetlands. This environment provided a suitable habitat for a wide array of terrestrial and marine prehistoric life, including various types of dinosaurs. The fossil record, though sparse due to the continent's extreme modern conditions and limited accessible rock exposures, offers compelling proof of this ancient reality. One of the most exciting and definitive discoveries affirming Antarctica as a dinosaur land came in 1986, with the unearthing of Antarctopelta oliveroi. This was the first definitive dinosaur fossil found on the continent, identified as an armoured dinosaur, a type of ankylosaur. Its remains were found on James Ross Island, off the tip of the Antarctic peninsula. Antarctopelta was a large, heavily built quadrupedal herbivore, covered in bony plates and spikes, providing protection against predators. The discovery of an ankylosaur in Antarctica was significant because it confirmed that even heavily armoured terrestrial dinosaurs, which would have been slow-moving, thrived in this region. This implies that the environment was sufficiently vegetated to support such large herbivores, and that there were no significant geographical barriers or extreme climates to prevent their widespread distribution across Gondwana. The fossil dates to the late Cretaceous period, approximately 84 to 72 million years ago, a time when Antarctica was still well connected to South America and Australia. Another momentous discovery was that of Cryolophosaurus elioti, a large carnivorous theropod dinosaur found in 1991 in the Transantarctic Mountains at Beardmore Glacier. Cryolophosaurus lived during the early Jurassic period, approximately 190 million years ago, making it one of the earliest large predatory dinosaurs known from the Jurassic. It was a bipedal carnivore, estimated to be about 6 to 8 meters, or 20 to 26 feet, long, with a distinctive thin, bony crest on its head, giving it the name frozen crested lizard. The discovery of Cryolophosaurus indicated that large active predators were present in Antarctica during the early Jurassic, suggesting a robust food web supporting both herbivores and carnivores. Its presence also highlights the interconnectedness of landmasses in Gondwana, as similar theropods have been found on other continents that were once part of the supercontinent. Beyond these well-known examples, other types of dinosaurs have also left their traces in Antarctica. Evidence of ornithopods, a group of herbivorous dinosaurs that includes the famous duck-billed hadrosaurs, has been found on the Antarctic peninsula. For instance, Trinisaurus santamartaensis, a small ornithopod, was described from the late Cretaceous period. The presence of these plant-eating dinosaurs further supports the notion of abundant vegetation. While complete skeletons are rare, isolated bones and fragments continue to be discovered, pointing to a diverse dinosaurian fauna. Although less extensively documented than theropods or ornithopods, there is also indirect evidence, such as footprints and fragmented bones, suggesting the presence of sauropods, the enormous long-necked quadrupedal herbivores in ancient Antarctica. Their existence would require vast amounts of plant material, again reinforcing the idea of a lush environment. The term dinosaur land for ancient Antarctica extends beyond just dinosaurs to include other remarkable prehistoric creatures that coexisted with them. Marine reptiles were abundant in the waters surrounding the continent. Plesiosaurs, long-necked marine predators, and mosasaurs, powerful marine lizards, patrolled the ancient seas, hunting fish and other marine life. Fossils of these reptiles, including partial skeletons and isolated bones, have been found in marine sedimentary rocks on the Antarctic peninsula. These discoveries confirm that the waters around ancient Antarctica were part of a globally interconnected ocean ecosystem, teeming with large predatory marine life. Flying reptiles, or pterosaurs, also soared through the skies above Antarctica. While direct fossil evidence is scarce, fragmentary remains and logical dispersal patterns suggest their presence, feeding on fish or small terrestrial animals. Early birds too inhabited ancient Antarctica. The discovery of Vegavis ii, a fossil bird from the late Cretaceous period found on Vega Island off the Antarctic peninsula, is particularly significant. Vegavis is one of the most complete early bird fossils from the southern hemisphere, and it provides crucial insights into the evolution of modern bird lineages. Its presence indicates that diverse avian life was part of the Antarctic ecosystem during the Dinosaur age. The fossil record also reveals a variety of other vertebrates that lived alongside dinosaurs. Evidence of early mammals, typically small and nocturnal creatures, has been found. These include multituberculates, an extinct group of rodentary mammals, and possibly early marsupial relatives. Amphibians also existed, exemplified by the discovery of Cryostega, a large temnospondyle amphibian from the Triassic period, roughly 250 million years ago, found in the Transantarctic mountains. The presence of such an amphibian, which requires freshwater bodies, indicates the existence of rivers, lakes, and wetlands during that time. Crocodilians, represented by fossils like Antarctosuchus, also inhabited ancient Antarctica during warmer periods, further confirming the mild, wet conditions, as modern crocodiles are intolerant of cold. Freshwater fish fossils have been found in ancient river and lake deposits, providing another layer of evidence for a robust aquatic ecosystem. Beyond vertebrates, various invertebrates, including insects, spiders, and mollusks, would have formed the base of many food webs, although their fossil record is less complete. The paleo-environmental reconstruction based on these fossil discoveries paints a clear picture of a strikingly different Antarctica. During the Mesozoic era, the continent lacked permanent ice sheets and supported extensive forests, ranging from conifer-dominated woodlands to lush fern-filled understories, as discussed in the Ancient Forests section. Rivers flowed freely, draining into coastal wetlands and lakes, providing essential habitats for amphibians and freshwater fish. The climate was warm and humid, enabling the sustained growth of the vegetation necessary to support large herbivorous dinosaurs. Even though Antarctica was at high latitudes, the global climate was generally much warmer, and the absence of the circumantarctic currents meant that warmer ocean water could reach its shores, preventing glaciation. While the high latitude meant extended periods of daylight in summer and prolonged darkness in winter, the animals and plants living there would have adapted to these unique light cycles. Some dinosaurs might have engaged in seasonal migrations to warmer regions or adapted to overwintering strategies, though the exact nature of their coping mechanisms is still an area of research. The fossil correlations across the former Gondwanan continents are pivotal to understanding the dinosaur land of Antarctica. The discovery of similar dinosaur species, such as specific types of sauropods or theropods, on multiple Gondwanan landmasses, South America, Africa, India, Australia, and Antarctica, provides compelling evidence for land connections and relatively unimpeded faunal exchange among these continents before their complete separation. These fossil distribution patterns helped solidify the theory of continental drift and provided insights into the biogeography of ancient animal populations. For example, the presence of certain dinosaur families in both South America and Antarctica indicates that land bridges persisted for significant periods during the Mesozoic, allowing animals to move freely between these land masses. This interconnectedness contrasts sharply with Antarctica's modern isolation. The end of the dinosaur era in Antarctica, as elsewhere on Earth, was marked by the Cretaceous Paleogene, or KPG, extinction event approximately 66 million years ago. This catastrophic event, widely attributed to the impact of a large asteroid, led to the demise of non-avian dinosaurs globally, including those in Antarctica. Following this immediate catastrophe, a gradual and profound climatic shift began to transform Antarctica into its current icy state. The continent's continued southward drift and, crucially, the final separation from Australia and South America led to the formation of the Antarctic Circumpolar Current. This current thermally isolated the continent, causing a dramatic and sustained cooling trend that eventually led to the growth of the massive ice sheets. As the climate became progressively colder, the forests retreated and the environment became inhospitable for large ectothermic reptiles like dinosaurs and crocodilians. Their niches were eventually filled by cold-adapted birds, seals and whales, and the terrestrial landscape became a realm dominated by ice. The challenges of discovering dinosaur fossils in Antarctica are formidable. Only a small fraction of the continent's landmass is exposed and accessible, primarily along the Antarctic Peninsula, the Transantarctic Mountains, and certain coastal islands. The vast interior is covered by kilometers of ice, making direct access to fossiliferous rock layers impossible. Fieldwork in these exposed areas is conducted under extremely harsh conditions, involving biting cold, fierce winds, blizzards, and remote logistical challenges. Transporting heavy equipment and fossil specimens is also a significant undertaking. The short field seasons, limited to the Antarctic summer, restrict the amount of time available for exploration. Despite these difficulties, dedicated paleontologists continue to brave the elements, slowly but surely piecing together the ancient history of Antarctica's life. The significance of Antarctica as a dinosaur land is multifaceted. Firstly, it provides crucial data for understanding the global distribution of dinosaurs and other prehistoric life, supporting and refining theories of Gondwana paleogeography and biogeography. The presence of these ancient animals confirms that life was widespread across the planet, even in high-latitude regions during warmer climatic periods. Secondly, it offers powerful evidence for Earth's dramatic climate shifts over geological time. The transition from a lush forested continent supporting dinosaurs to an ice-covered wasteland demonstrates the profound impact of long-term climate changes driven by plate tectonics and atmospheric composition. Thirdly, the fossils provide unique insights into the adaptations of ancient life to high-latitude conditions, such as seasonal light cycles, even in the absence of extreme cold. Finally, these discoveries continue to inspire scientific exploration and public interest in one of Earth's most mysterious continents, revealing its rich and dynamic past that contrasts so sharply with its frozen present. The buried bones and ancient tracks tell a story of a vibrant living continent long before the grip of the ice took hold. The vast ice sheets of Antarctica serve as an unparalleled archive of Earth's past climate, acting like natural time capsules that preserve invaluable data over hundreds of thousands, and in some cases, millions of years. This remarkable record is contained within ice cores, long cylinders of ice drilled from deep within the continental ice sheets. Each layer of snow that falls on Antarctica accumulates and gradually compacts, transforming first into firn, a granular intermediate stage, and then into dense glacial ice. As this transformation occurs, the ice encapsulates tiny bubbles of ancient air, dust particles, volcanic ash, and various chemical impurities, all of which provide crucial clues about the environmental conditions at the time the snow originally fell. Scientists meticulously extract and analyze these ice cores to reconstruct Earth's ancient climate, atmospheric composition, and records of past events like volcanic eruptions, offering a profound understanding of natural climate variability before significant human impact. The formation of an ice core as a time capsule is a continuous process that occurs over millennia. Every year, new snow falls on the surface of the ice sheet, adding a fresh layer. In regions of high accumulation and relatively stable ice flow, these annual layers can often be visually distinguished, much like tree rings. As subsequent layers of snow pile up, the weight of the overlying snow compresses the layers beneath. This compression gradually transforms the light, fluffy snow into denser, granular firn, typically at depths ranging from 50 to 100 meters, or about 160 to 330 feet, depending on temperature and accumulation rates. During this finification process, the air spaces between the snow crystals become smaller and less connected to the atmosphere. Finally, as the pressure increases further, typically beyond 100 meters, the firn fully compacts into solid, impermeable glacial ice, trapping the remaining air within discrete sealed bubbles. These trapped air bubbles contain pristine samples of the Earth's atmosphere from the time they were sealed, preserving the exact composition of the air from that ancient era. Retrieving these invaluable time capsules involves highly specialized ice core drilling operations. Scientists establish remote field camps in the coldest and highest regions of the Antarctic ice sheet, far from coastal melting influences. Deep ice core drilling programs, often international collaborations, use sophisticated drilling rigs to bore vertically into the ice. The drill bits are designed to cut a cylindrical core of ice, which is then brought to the surface in sections, typically 3 to 4 meters or 10 to 13 feet long. Each section is meticulously handled, logged, cut, and stored in ultra-cold conditions, usually minus 20 degrees Celsius or minus 4 degrees Fahrenheit, or colder, to prevent melting or alteration of the delicate chemical and gas records. The deepest ice cores drilled in Antarctica have penetrated more than 3.5 kilometers, or over 2 miles, into the ice, reaching ice that is over 800,000 years old. The challenges of drilling are immense, including battling extreme cold, high winds, logistical complexities of transporting heavy equipment, and the paramount need to prevent contamination of the ice core samples from modern air or drilling fluids. One of the most critical pieces of climate information derived from ice cores is ancient temperature data. This is primarily reconstructed by analysing the ratios of stable isotopes of water molecules trapped within the ice. Water molecules are composed of hydrogen and oxygen atoms. While most water molecules contain common hydrogen and oxygen-16, a small fraction contains heavier isotopes: deuterium, heavy hydrogen, also known as hydrogen-2, and oxygen-18. The ratio of these heavy isotopes to their lighter counterparts in the ice, specifically the ratio of oxygen, 18 to oxygen-16, or deuterium to hydrogen-1, varies systematically with temperature. During colder periods, the lighter isotopes evaporate more easily from the ocean and are preferentially transported to the poles, resulting in ice that is depleted in heavy isotopes. Conversely, during warmer periods, more heavy isotopes are incorporated into the snow that falls on the ice sheet. By measuring these isotopic ratios along the length of an ice core, scientists can reconstruct past temperatures at the drill site, effectively creating a paleothermometer. These isotopic records provide detailed temperature reconstructions for past glacial and interglacial cycles, revealing the natural rhythm of Earth's climate over hundreds of thousands of years. Beyond temperature, ice cores provide direct measurements of Earth's ancient atmospheric composition, particularly the concentrations of greenhouse gases. The air bubbles trapped within the ice are literal samples of the ancient atmosphere. Scientists can extract this trapped air by carefully crushing or melting sections of the ice core in a vacuum chamber, and then analyze the gas composition using mass spectrometry and gas chromatography. This allows for precise measurements of past concentrations of critical greenhouse gases, including carbon dioxide, methane, and nitrous oxide. The longest ice core records show that for the past 800,000 years, during natural glacial-interglacial cycles, atmospheric carbon dioxide concentrations naturally fluctuated between approximately 180 parts per million during cold glacial periods and about 280 parts per million during warm interglacial periods. Methane and nitrous oxide also followed similar patterns. The remarkable finding from ice core data is the strong and consistent correlation between these greenhouse gas concentrations and global temperatures over these vast timescales. When carbon dioxide and methane levels were high, temperatures were warm. When they were low, temperatures were cold. This provides compelling evidence for the role of greenhouse gases in regulating Earth's climate. Ice cores also contain a remarkable record of atmospheric dust. Fine particles of dust, originating from arid regions and deserts across the globe, are transported by winds and deposited on the ice sheet along with snow. The concentration and size of dust particles preserved in ice cores provide clues about past atmospheric circulation patterns wind strength, and the extent of arid regions globally. During cold glacial periods, ice cores generally show much higher dust concentrations than during warm interglacial periods. This is attributed to several factors: stronger winds during colder, more arid conditions, larger exposed desert areas, and reduced vegetation cover in source regions, allowing more dust to be entrained into the atmosphere. The analysis of dust provides insights into past aridity, changes in global wind systems, and potential impacts of dust on climate, such as its effect on the Earth's albedo, or reflectivity, or its role as a nutrient source for marine ecosystems when deposited in the ocean. Volcanic activity is another major category of climate clues preserved in ice cores. Large volcanic eruptions inject vast amounts of gases and particulate matter into the atmosphere, which can have significant, albeit temporary, impacts on global climate. Ice cores preserve two primary types of volcanic records. Firstly, visible layers of volcanic ash, or tephra, from specific eruptions can be identified within the ice. These ash layers act as precise chronological markers, allowing scientists to correlate ice core records with other geological archives, such as lake sediments or marine cores. Secondly, and more importantly for climate studies, ice cores record the deposition of volcanic aerosols, primarily sulfates. Large explosive eruptions inject sulfur dioxide into the stratosphere, where it oxidizes to form sulfuric acid aerosols. These aerosols reflect incoming solar radiation, leading to a temporary cooling of Earth's surface. As these aerosols slowly fall back to Earth, they are incorporated into the snow layers. Scientists measure the acidity levels in ice cores, or the concentrations of specific ions like sulfate, to reconstruct the history of major volcanic eruptions. These records provide a timeline of past volcanic activity and their cooling effects, allowing researchers to distinguish between natural volcanic cooling events and longer-term climate trends. Beyond gases, dust, and volcanic signals, ice cores also provide insights into past solar activity. Cosmogenic isotopes, such as beryllium-10, are produced in the Earth's atmosphere by cosmic rays. The production rate of beryllium-10 is influenced by solar activity. During periods of high solar activity, the Sun's magnetic field shields Earth from cosmic rays, reducing beryllium-10 production. Conversely, during periods of low solar activity, more cosmic rays reach Earth's atmosphere, leading to higher beryllium-10 production. Once produced, beryllium-10 atoms attach to aerosols and fall to Earth, eventually becoming incorporated into ice sheets. By measuring the concentration of beryllium-10 in ice cores, scientists can reconstruct past variations in solar activity over thousands of years. These records help to assess the influence of solar variability on Earth's climate system, allowing researchers to compare the relative contributions of solar forcing versus other factors like greenhouse gases to past climate changes. Ice cores also hold chemical proxies that provide clues about past sea ice extent. For example, methane sulfonic acid, or MSA, is a compound produced by marine algae that thrive in sea ice environments. When these algae are active, they release MSA into the atmosphere, which is then transported by winds and deposited in snow. Higher concentrations of MSA in ice cores can indicate periods of more extensive sea ice cover around Antarctica. By reconstructing past sea ice extent, scientists can understand how this critical component of the polar environment has responded to past climate changes and its role in ocean circulation and energy exchange. Other chemical species found in ice cores, such as sodium and chloride ions from sea salt, nitrate and ammonium, provide additional information about past atmospheric chemistry, ocean productivity, and even the frequency of forest fires on other continents. These chemical fingerprints add layers of detail to the multidimensional climate record preserved in the ice. Accurately dating ice cores is fundamental to their utility as climate archives. The most precise dating method for the upper sections of ice cores is annual layer counting. This involves identifying distinct seasonal variations in physical properties, such as dust layers, more in winter, less in summer, acidity, higher after volcanic eruptions, or stable isotope ratios, seasonal temperature shifts. By counting these annual layers, scientists can establish a precise chronology for the upper tens of thousands of years of the ice core record. For deeper, older ice, where annual layers become too thin to distinguish due to ice compaction and flow, scientists rely on ice flow models. These models account for the thinning and stretching of ice layers as they are compressed and flow towards the edges of the ice sheet. Volcanic horizons, where distinct ash layers from known eruptions are found in multiple ice cores or other geological records, serve as important tie points for cross-dating different ice cores and calibrating ice flow models. The dating of the air bubbles trapped within the ice is slightly different from the dating of the ice itself, as gases take some time to be fully trapped as firn compacts into ice. This difference, known as the gas age-ice age difference, must be carefully accounted for in climate reconstructions. Several major international ice core projects have provided the foundational data for our understanding of ancient climate. The Vostok ice core, drilled by Russian scientists in East Antarctica, provided the first continuous climate record spanning over 400,000 years, revealing 4 complete glacial-interglacial cycles. This record was groundbreaking, clearly demonstrating the natural cycles of carbon dioxide and methane in the atmosphere correlating with temperature. The European project for ice coring in Antarctica, known as EPICA, drilled at Dome Sea in East Antarctica, extended this record to an astonishing 800,000 years, encompassing 8 glacial-interglacial cycles. This longer record confirmed the patterns observed at Vostok and provided even more detailed insights into climate variability over this period. More recently, the West Antarctic Ice Sheet Divide ice core, known as WBS Divide, drilled by American scientists, provided a very high-resolution record spanning the last 68,000 years, covering the last glacial period and the transition to the current interglacial. Its high resolution allows for a much finer examination of rapid climate shifts. Scientists are now actively searching for even older ice, potentially 2 to 3 million years old, which could provide insights into a period of Earth's climate when carbon dioxide levels were similar to those of the present day, before human industrialization. The significance of ice cores as climate clues cannot be overstated. They provide the most direct and continuous records of past atmospheric composition and temperature, which are essential for understanding natural climate variability. This understanding allows scientists to distinguish between natural climate changes and those caused by human activities. For instance, ice core data unequivocally show that current atmospheric carbon dioxide and methane concentrations are far higher than anything seen in the last 800,000 years, and their rates of increase are unprecedented in the natural record. This provides a crucial baseline against which modern climate change can be assessed. Ice core data are also vital for calibrating and validating climate models, ensuring that these complex computer simulations can accurately reproduce past climate conditions before being used to forecast future changes. By looking back in time through the layers of ice, scientists gain invaluable insights into the Earth's delicate climate system, helping to inform decisions about our planet's future. The current frozen state of Antarctica is not merely a consequence of its high latitude, but is profoundly influenced by its geological history, particularly the movement of Earth's tectonic plates. Over hundreds of millions of years, the slow but relentless motion of these massive crustal plates has reshaped the continents, opened and closed ocean basins, and ultimately dictated Antarctica's journey to the South Pole. This tectonic journey fundamentally influenced global ocean circulation and atmospheric patterns, setting the stage for the continent's transformation from a lush, forested land to the ice-covered realm we know today. Understanding these tectonic shifts is crucial for grasping why Antarctica is so heavily glaciated and how its position influenced its glaciation process. Antarctica's story begins as a central component of Gondwana, a vast supercontinent that existed from roughly 600 million years ago until its fragmentation began around 180 million years ago. During the Paleozoic and early Mesozoic eras, Antarctica was connected to South America, Africa, India, Australia, and Zealandia, a submerged continent that includes New Zealand. This continental configuration meant that Antarctica was situated at higher latitudes compared to other landmasses, but it was still part of a much larger landmass that affected global climate. During this period, the Earth generally experienced warmer temperatures than today, and there were no significant permanent ice sheets on Antarctica. Geological evidence, including abundant fossil forests and dinosaur remains, confirms that ancient Antarctica enjoyed a mild, temperate climate, far too warm for widespread glaciation. The absence of ice was due to the continental configuration and higher atmospheric carbon dioxide levels. The fragmentation of Gondwana was a series of pivotal tectonic shifts that spanned tens of millions of years, gradually isolating Antarctica. The initial stages of this breakup began in the Jurassic period, around 180 million years ago, with the separation of Africa and India from the vast Gondwanan landmass. This created the nascent Indian Ocean and South Atlantic Ocean. During this time, East Gondwana, comprising Antarctica, Australia and Zealandia, remained largely connected. The climate, though perhaps experiencing slight cooling compared to the super warm periods, remained generally warm enough to sustain extensive conifer forests and diverse dinosaur populations in Antarctica. The newly formed ocean basins, while growing, did not yet create the conditions necessary for widespread glaciation at high southern latitudes. The most critical tectonic events for Antarctica's glaciation occurred in the mid-Cenozoic era, particularly during the Paleogene period. The first key separation involved Australia and Zealandia from Antarctica. This rifting process led to the opening of the Tasman Gateway, a seaway between Antarctica and Australia, beginning around 53 million years ago during the Eocene epoch. While initially narrow and shallow, this opening allowed for some degree of water circulation between the Pacific and Indian Oceans at southern latitudes. This was an important step towards the thermal isolation of Antarctica, but it was not yet enough to trigger full-scale continental glaciation. The separation was a slow process, with continental fragments gradually drifting apart, altering oceanic bathymetry and creating new oceanic crust. The final and arguably most decisive tectonic shift for Antarctica's climate was the opening of the Drake Passage, the deep water channel between South America and the Antarctic Peninsula. Geological evidence suggests that the Drake Passage began to open around 45 to 34 million years ago near the Eocene-Oligocene boundary. This opening was a gradual process, with initial shallow seaways becoming progressively deeper and wider over millions of years. The completion of the deep-water Drake Passage, allowing unrestricted ocean flow, is widely believed to have occurred around 34 million years ago. This event had profound and immediate consequences for global ocean circulation, and consequently, for Antarctica's climate. The completion of the Drake Passage and the Tasman Gateway allowed for the establishment of the Antarctic Circumpolar Current, or ACC. This powerful ocean current flows eastward around the entire continent of Antarctica, unobstructed by any major landmass. The formation of the ACC created an oceanic thermal fence around Antarctica, effectively isolating the continent from warmer subtropical waters. Before the ACC, warm ocean currents from lower latitudes could reach and warm Antarctica's coasts, preventing the widespread accumulation of ice. With the ACC in place, warm water was largely diverted northward, while cold, dense waters circulated continuously around Antarctica, chilling its coasts. This thermal isolation was the primary oceanic mechanism that drove Antarctica into its present deep freeze. The sheer volume and speed of the ACC, which is the largest ocean current on Earth, make it incredibly effective at maintaining this thermal barrier. The formation of the Antarctic Circumpolar Current, triggered by these tectonic shifts, had a cascading effect on global climate. It led to a significant intensification of global cooling, transforming Earth from a largely greenhouse world of the Mesozoic and early Cenozoic into an icehouse world characterized by continental glaciation. The cold waters of the Southern Ocean, now isolated from warmer currents, became even colder, contributing to the formation of dense, cold bottom waters that spread throughout the world's oceans, influencing global ocean circulation patterns. This shift in ocean currents significantly impacted heat distribution across the planet, making high latitudes, particularly the South Pole, much colder. This was a critical step in setting the stage for the growth of massive ice sheets. Coupled with these tectonic and oceanic changes were longer-term trends in atmospheric carbon dioxide levels. Over tens of millions of years, particularly since the mid-Cenozoic, global atmospheric carbon dioxide concentrations gradually decreased, primarily due to natural processes such as the increased weathering of silicate rocks on continents, which consumes carbon dioxide from the atmosphere. The uplift of major mountain ranges like the Himalayas can accelerate this weathering. This gradual decline in atmospheric carbon dioxide contributed to a long-term global cooling trend. While orbital cycles of Earth around the Sun, known as Milankovitch cycles, cause shorter-term fluctuations in climate and trigger glacial and interglacial periods, the long-term tectonic configuration and declining carbon dioxide levels provided the fundamental context that allowed for the initial and sustained glaciation of Antarctica. The tectonic isolation of Antarctica ensured that even slight decreases in global temperature or changes in orbital forcing would lead to significant ice accumulation on the continent. The onset and evolution of Antarctic glaciation directly followed these critical tectonic shifts. Around 34 million years ago, at the Eocene-Oligocene boundary, significant continental-scale glaciation began on Antarctica. Initially, this involved the formation of small ice caps on high-altitude mountain ranges, such as the Transantarctic Mountains, which due to their elevation were naturally cooler. As temperatures continued to drop due to oceanic isolation and declining carbon dioxide, these smaller ice caps expanded and coalesced, eventually growing into the vast East Antarctic ice sheet. The East Antarctic ice sheet, being the larger and geologically older part of the continental ice, formed first and has remained relatively stable for millions of years. The West Antarctic ice sheet, in contrast, formed later, is generally thinner and rests largely on bedrock below sea level, making it more dynamic and potentially more sensitive to changes in ocean temperature. The continued presence and stability of these ice sheets were directly facilitated by Antarctica's eventual position directly over the South Pole, an arrangement largely dictated by its tectonic journey. The growth of the ice sheets also initiated powerful positive feedback loops. As more snow and ice accumulated covering the dark land surface, the continent's albedo, or reflectivity, significantly increased. Ice and snow reflect a large proportion of incoming solar radiation back into space, whereas darker land or ocean surfaces absorb more. This increased reflection led to further cooling of the continent, which in turn promoted more ice growth, further increasing albedo in a self-perpetuating cycle. This ice albedo feedback mechanism played a crucial role in rapidly transforming Antarctica into its present glacial state, once the initial cooling threshold was crossed. The combined effect of tectonic isolation, declining atmospheric carbon dioxide, and positive feedback loops locked Antarctica into its icy fate. The underlying topography of Antarctica, also shaped by tectonic processes, further influenced its glaciation. Mountain ranges like the Transantarctic Mountains and the Gamburtsev Mountains, which were formed by past tectonic activity, acted as initial nucleation points for ice accumulation. Their high elevations allowed snow to persist and turn into ice even during periods when lower elevations were still ice-free. These mountains later acted as barriers or guides for the flowing ice, channeling its movement towards the ocean. Conversely, major tectonic rift systems, such as the West Antarctic Rift System, which is still geologically active today, created vast basins and valleys beneath the ice. These deep basins can influence ice flow patterns, potentially making overlying ice sheets more vulnerable to warming ocean waters, especially if they're grounded below sea level. The tectonic history thus not only positioned Antarctica at the pole, but also sculpted the very land on which the ice sheets grew and flow.